Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists both in the realm of scientific fact and cosmic mystery. I want to take you on a journey through space and time, following the path of a visitor that came to us from beyond our solar system, a messenger from the depths between stars. You might have heard its name whispered in scientific circles, or seen it mentioned in passing. 3I Atlas, that enigmatic interstellar comet that graced our cosmic neighborhood not so long ago. It's a name that might seem clinical, perhaps even forgettable. But behind those letters and numbers lies one of the most profound questions we can ask ourselves as we drift off into the peaceful darkness of sleep tonight. What if this visitor, this ancient traveler from another star system entirely, wasn't just passing through? What if, in the grand cycles of the cosmos, it comes again? Now, I know what you might be thinking as you settle into your comfortable position, perhaps adjusting your pillow just so, finding that perfect spot where your body can fully relax. You might be thinking that space is so vast, so incomprehensibly enormous, that the chances of anything returning seem impossibly small. And you would be right to think that. The universe is indeed vast beyond our ability to truly comprehend. But that's precisely what makes this contemplation so wonderfully mysterious, so perfectly suited for these quiet hours when our minds can wander freely through the cosmos without the constraints of our daily concerns. Because in the mathematics of infinity, in the endless dance of gravity and momentum, even the most unlikely returns become possible, perhaps even inevitable given enough time. Before we dive deeper into this cosmic mystery, I'd like to share something with you, something that connects us all to this story in a very personal way. You see, every night when you look up at the stars, if you're fortunate enough to have clear skies above you, you're participating in an ancient human tradition that stretches back to the very dawn of consciousness. Our ancestors looked up at these same stars, perhaps not understanding what they were seeing in the scientific sense we do today, but feeling that same sense of wonder, that same pull toward the infinite. And occasionally, just occasionally, they would see something different moving among those fixed points of light. A visitor, a wanderer, a messenger from somewhere else entirely. Tonight, as you listen to these words and let your mind drift among the stars, you're continuing that tradition. You're part of an unbroken chain of cosmic observers stretching back through all of human history. And speaking of being part of something larger, I want to mention that if you find yourself drawn into this cosmic journey, if these mysteries spark something in your imagination, you might consider subscribing to hear more of these nighttime explorations. There's something beautiful about knowing that others around the world are drifting off to sleep contemplating the same vast questions, the same infinite possibilities. It creates a kind of gentle community of dreamers and wanderers, all of us connected by our shared curiosity about the cosmos. But for now, let's return to our visitor, to 3I Atlas, and begin to understand what makes it so special, so unique among all the objects we've observed in our solar system. The story of 3I Atlas begins not with its discovery, but billions of years before, in a star system we will likely never see with our own eyes, around a sun that might no longer even exist. Imagine, if you will, a young star system, perhaps not so different from our own when it was in its youth. Planets are forming from the swirling disk of dust and gas, colliding and coalescing, building themselves up grain by grain, boulder by boulder, into the worlds they will become. And in the outer reaches of this system, where the sun's warmth barely reaches, ice and rock come together to form countless small bodies, comets, frozen time capsules that will preserve the chemical signature of their birthplace for eons to come. Now, in most star systems, these comets remain bound to their parent star, orbiting in vast elliptical paths that might take them far from their sun, but always, always bring them back. They're like cosmic yo-yos, forever tethered by the invisible string of gravity. But sometimes, just sometimes, something extraordinary happens. Perhaps it's a close encounter with a massive planet, its gravity acting like a cosmic slingshot. Perhaps it's the gravitational influence of a passing star disrupting the delicate orbital balance. Or perhaps it's something even more exotic, more mysterious. Whatever the cause, occasionally one of these frozen wanderers receives just enough of a push, just enough additional velocity to break free from its stellar bonds entirely. And this is what happened to the object we now call 3I Atlas. Somewhere in the distant past, in a moment of cosmic coincidence or inevitability, this chunk of ice and rock and organic compounds achieved escape velocity. It broke free from whatever star system gave it birth and began a journey that would last billions of years, crossing the unimaginable emptiness between stars. Can you imagine that? Billions of years of silence, of darkness, of absolute cold. While on Earth, life was just beginning to emerge from the primordial seas, while the first complex cells were learning to work together, while dinosaurs rose and fell, while humanity took its first tentative steps, this object was sailing through the void, carrying within its frozen heart the secrets of another world entirely. The designation 3 Atlas tells us something important about our visitor. The I stands for interstellar, marking it as only the third confirmed object from beyond our solar system that we've been able to observe passing through. The first was Oumuamua, that strange, elongated object that captured the world's imagination with its unusual properties and trajectory. The second was 2I Borisov, a more typical comet but still a messenger from the stars, and then came 3I Atlas, discovered by the Asteroid Terrestrial Impact Last Alert System, hence the Atlas in its name. Each of these objects is precious to us, scientifically speaking, because they represent our only opportunity to study material from other star systems without having to travel there ourselves. When astronomers first spotted 3I Atlas, it was just a faint smudge of light moving against the background stars, barely distinguishable from the countless asteroids and comets that belong to our own solar system. But as they tracked its motion, calculated its trajectory, something remarkable became clear. This object was moving too fast, far too fast to be bound to our sun. It was following a hyperbolic orbit, a path that would bring it swooping through our solar system once and only once, before sending it back out into interstellar space. Unless, of course, we consider the possibilities that the vast cycles of the galaxy might offer, the strange attractions and perturbations that occur over cosmic timescales. Think about the path this object has taken to reach us. In the billions of years since it left its home star, 3I Atlas has been subject to the gentle but persistent gravitational tugs of every star it has passed, every massive object it has encountered. Each interaction, no matter how slight, has altered its trajectory just a tiny bit. It's like a cosmic pinball, bouncing not off physical barriers but off invisible wells of gravity, each encounter sending it in a slightly different direction. And somehow, through all of that chaos, all of that randomness, its path intersected with our solar system at precisely the right time for us to observe it. The odds of this happening are so astronomically small that it's almost easier to think of it in terms of destiny rather than chance. But that's the thing about the universe. Given enough space and enough time, even the most improbable events become certainties. Somewhere out there right now, there are countless other interstellar objects sailing through the darkness. Most of them will never come close enough to any star system for anyone or anything to observe them. They'll spend eternity in the cold and the dark, carrying their secrets with them. But a few, just a precious few, will have encounters like 3I Atlas did with us. When we detected 3I Atlas, it was already beginning its approach toward the inner solar system. Like all comets, as it drew closer to our sun, it began to wake up from its billions-year slumber. The increasing warmth caused the ices that had been frozen solid since before Earth existed to begin sublimating, turning directly from solid to gas. This created the characteristic coma and tail that we associate with comets, that beautiful glowing cloud that has inspired wonder and occasionally fear throughout human history. But unlike the comets from our own solar system, the gases and dust streaming off 3I Atlas carried information about conditions in another star system entirely. Scientists rushed to observe our visitor with every instrument available. Telescopes around the world and in space turned their attention to this interstellar wanderer. Spectrographs analyzed the light reflecting off its surface and passing through its coma, revealing its chemical composition. Radio telescopes listened for any unusual signals, though none expected to find evidence of anything artificial. This was our chance, possibly our only chance in our lifetimes, to study material from another star system up close. Well, relatively up close. Even at its nearest approach, 3 Atlas was still millions of miles away from Earth. What we learned from these observations was both fascinating and tantalizing. The comet's composition was similar in many ways to comets from our own solar system, suggesting that the basic processes of planet and comet formation might be universal. It contained water ice, carbon dioxide, and various organic compounds, the same building blocks of life that we find in our own cosmic neighborhood. But there were subtle differences too. Isotopic ratios that didn't quite match what we're used to seeing, trace elements in unexpected proportions. These differences are like a fingerprint, a unique signature that could, if we knew how to read it properly, tell us about the conditions in 3I Atlas's home star system. Perhaps even more intriguing was the comet's behavior as it passed through our solar system. Like Oumuamua before it, 3I Atlas showed some unexpected accelerations that couldn't be entirely explained by the gravitational forces acting on it. Some of this could be attributed to outgassing, the jet-like effect created as ices sublimate and shoot gas and dust into space. But the details didn't quite match our models. It's as if these interstellar visitors follow slightly different rules than the comets we're familiar with. Or perhaps they're trying to tell us that our understanding of comet behavior is still incomplete. As you lie there in the darkness, perhaps you can imagine yourself as a passenger on 3I Atlas, riding this ancient chunk of ice and rock as it swoops through our solar system. From your perspective on the comet, the sun would grow from just another star, perhaps slightly brighter than the others, to a blazing orb that dominates the sky. You would pass by the outer planets, Neptune and Uranus, barely visible as pale dots, then Jupiter and Saturn, magnificent even from millions of miles away. You might catch a glimpse of Mars, that red wanderer that has captured human imagination for millennia, and then Earth, our pale blue dot, the only known harbour of life in the universe. But your visit would be brief, cosmically speaking. After just a few months in the inner solar system, you would be flung back out into the darkness, the sun shrinking behind you until it was once again just another star among billions, and ahead of you, another billion years of travel, perhaps more, before your next encounter with a star system. Where will you go? What will you see? These are questions we can only imagine the answers to, but that's what makes them perfect for contemplation as we drift towards sleep. Now, here's where our story takes an even more intriguing turn. You see, when we talk about 3I Atlas or any interstellar object leaving our solar system, we're using that term in a very specific, limited way. We mean that it's no longer bound by our sun's gravity, that it's on an escape trajectory that will carry it back into interstellar space. But the universe is not a static place. Everything is in motion. Our sun orbits the center of the Milky Way galaxy, taking about 230 million years to complete one circuit. The galaxy itself is moving through space, approaching our neighbor Andromeda at tremendous speed. And all the while, the stars around us are moving too, following their own orbital paths around the galactic center. What this means is that the concept of leaving and returning becomes much more complex when we consider cosmic timescales. An object that leaves our solar system today might, through the complex dance of stellar motions and galactic rotation, find its path intersecting with ours again in the far future. It's like two people walking in a vast forest. They might part ways at one point, each following their own path, but if the forest has circular trails, if there are patterns to the paths, they might meet again, perhaps without even realizing they've encountered each other before. This is the beautiful mystery we're contemplating tonight. What if Three-Eye Atlas, through some cosmic coincidence, or perhaps through the inevitable mathematics of orbital mechanics on a galactic scale, comes again? Not tomorrow, not in our lifetimes, probably not even in the lifetime of our species as we currently exist. But perhaps in millions of years, when Earth is a very different place, when humanity has either evolved into something unrecognizable or spread among the stars, this ancient traveller might return to our neighbourhood. The physics of such a return are actually fascinating to consider, and I mean that in the most gentle, wonder-inducing way possible. You see, our galaxy is not a rigid structure. It's more like a vast whirlpool of stars, gas and dark matter, all rotating around a common centre. But different parts of the galaxy rotate at different speeds. Stars closer to the centre complete their orbits faster than those farther out. This is called differential rotation, and it means that the relative positions of stars are constantly changing. Imagine you're watching a very slow, very beautiful cosmic dance. Each star is a dancer, following its own path, but all a part of the same grand performance. Sometimes dancers that were far apart come close together. Sometimes those that were close drift apart, and sometimes, just sometimes, dancers that parted ways earlier in the performance find themselves close together again, as if the choreography of gravity had planned their reunion all along. For Three Atlas to return to our solar system, it would need to follow a path through the galaxy that, after millions or billions of years, brings it back to wherever our sun happens to be at that time. This isn't impossible. In fact, given the way stars and other objects move through the galaxy, it's statistically likely that some objects do return to neighbourhoods they've visited before. They might not recognise these neighbourhoods, of course. Stars are born and die, planetary systems evolve, and the cosmic landscape is constantly changing. But the paths through space, the invisible highways carved by gravity and momentum, these remain, creating possibilities for return that we're only beginning to understand. There's something deeply comforting about this idea, don't you think? In our daily lives, we often feel like everything is rushing away from us, like opportunities missed are gone forever. But the universe operates on different principles. In the cosmos, nothing is ever truly lost. Energy cannot be created or destroyed, only transformed. Matter cycles through different forms but remains part of the cosmic inventory. And objects in motion continue in motion, following paths that, while complex and difficult to predict over long timescales, are ultimately governed by knowable laws. As we contemplate the possible return of Three-Eye Atlas, we're really contemplating something much deeper about the nature of existence itself. We're thinking about cycles and patterns, about the eternal return that philosophers have pondered for millennia. We're considering our place in a universe where timescales so vast that they dwarf human comprehension are just business as usual, where patience is measured not in years or centuries but in geological and cosmic epochs. Let me paint you a picture of what such a return might look like, not to alarm or excite, but simply to wonder at the possibilities. Imagine it's millions of years in the future. The Earth has changed dramatically. Continents have shifted. New mountain ranges have risen while others have worn away to nothing. The night sky looks different too. Some of the stars we see tonight have exhausted their fuel and faded to darkness. New stars have been born from vast clouds of gas and dust. The constellations our ancestors used to navigate and tell stories have morphed into new patterns entirely. And in this transformed world, whatever intelligent beings exist, perhaps our far distant descendants, perhaps something else entirely, detect a familiar visitor approaching. Not familiar because anyone remembers it, of course. Too much time has passed for that, but familiar because its chemical signature, its isotopic fingerprint, matches something in ancient records, data preserved through all the changes and chances of millions of years. Three Atlas has come again, carrying within its frozen heart the same messages from its original star system, plus new information gathered during its long journey through the galaxy. What stories could it tell, if we knew how to read them? What stars has it passed close to? What other planetary systems has it visited? Has it been captured temporarily by another star's gravity, spending some time as a distant, frozen member of an alien solar system before being flung free again? Has it collided with other objects, gathering or losing material, changing its composition in subtle ways? Each encounter would leave its mark, creating a kind of cosmic travel diary, written in ice and rock and organic molecules. The organic molecules are particularly intriguing to consider. We know that comets in our own solar system carry complex organic compounds, including amino acids, the building blocks of proteins. These aren't signs of life, but rather the natural products of chemistry occurring in the cold depths of space. But they're also the raw materials from which life, at least as we know it, assembles itself. When comets impact planets or moons, they deliver these organic compounds along with water and other volatiles. It's entirely possible that Earth's oceans and perhaps even the precursors to life itself were delivered by cometary impact early in our planet's history. Now, imagine 3i Atlas on its journey between star systems. It's not travelling through completely empty space. Even in the vast voids between stars, there are thin clouds of gas and dust. Individual atoms and molecules spread so thinly that you might travel for miles before encountering one. But over billions of years, even these rare encounters add up. The comet's surface, exposed to cosmic rays and the occasional atom or molecule, becomes a kind of chemical laboratory where slow reactions can occur, where new compounds can form. Perhaps, and this is pure speculation but beautiful to consider, 3i Atlas carries within it molecules that formed in the space between stars, compounds that exist nowhere else in the universe. These interstellar chemicals, formed under conditions we can barely replicate in our best laboratories, might hold keys to understanding chemistry in extreme environments. They might even include forms of complex organic molecules we've never seen before, assembled atom by atom over cosmic timescales in the cold darkness between stars. As you drift deeper into relaxation, letting these cosmic possibilities wash over you like gentle waves, consider how the story of 3i Atlas connects to larger patterns in the universe. Everything in the cosmos seems to move in cycles, from the smallest subatomic particles oscillating at incomprehensible frequencies to the largest structures in the universe slowly rotating and evolving over billions of years. Planets orbit stars, stars orbit galactic centers, galaxies move in clusters and superclusters, and perhaps even the universe itself goes through cycles of expansion and contraction. Though that's a mystery we're still working to understand. These cycles within cycles create a kind of cosmic rhythm, a heartbeat of the universe that pulses on timescales we can barely imagine. The return of an interstellar comet would be just one note in this vast symphony, but what a profound note it would be. It would remind us that the universe has a memory of sorts, that information can be preserved and transmitted across impossible distances and incomprehensible spans of time. It would show us that isolation is an illusion, that everything in the cosmos is connected through the invisible threads of gravity and the shared history of matter forged in the hearts of dying stars. Speaking of dying stars, it's worth contemplating the ultimate origin of 3i Atlas and objects like it. Every atom in the comet, except for hydrogen and helium which formed in the Big Bang, was created inside a star. The carbon that forms its organic molecules, the oxygen in its water ice, the silicon in its rocky components, all of these were forged through nuclear fusion in stellar cores. When those stars died, some peacefully shedding their outer layers, others in spectacular supernova explosions, they scattered these elements into space where they could become part of new star systems, new planets, new comets. This means that 3i Atlas is, in a very real sense, a messenger not just from another star system, but from multiple generations of stars. It carries within it the ashes of suns that died before our own sun was born. When we study its composition, we're reading a history that goes back to the early universe, to the first generations of stars that lit up the cosmic darkness. And if it returns in the distant future, it will still be carrying that history, plus whatever new chapters have been added during its journey through space and time. There's a beautiful symmetry to consider here. Just as 3i Atlas might return to our solar system in the far future, pieces of our own solar system are undoubtedly making similar journeys. Every so often, interactions between objects in the outer solar system result in comets or asteroids being ejected entirely, sent on interstellar trajectories of their own. These objects become our messengers to the cosmos, carrying information about our sun and planets to whoever or whatever might observe them in distant star systems. Imagine one of our comets, perhaps one that formed in the same era as Earth itself, arriving in an alien solar system millions of years from now. If there are astronomers there, beings curious about the universe beyond their own star, they would study our comet with the same fascination we showed for 3i Atlas. They would analyze its composition, marvel at its interstellar origin, and perhaps wonder about the star system it came from. Is there life there, they might ask? What stories could this frozen wanderer tell if only we knew how to listen? In this way, the universe becomes a vast communication network, with comets and asteroids as the messengers, carrying information between star systems at speeds that seem impossibly slow by human standards, but are perfectly reasonable on cosmic timescales. It's not the kind of communication we usually imagine when we think about contact between civilizations, no radio signals, no faster-than-light travel, no deliberate attempts at contact. Instead, it's a natural, patient, inevitable exchange of material and information, mediated by gravity and time. The possibility of 3i Atlas returning also raises profound questions about identity and continuity. If the comet does return millions of years from now, will it still be the same object? On one level, yes. It will still be the same collection of ice and rock and organic molecules, following the laws of physics through space. But it will also have been changed by its journey. Cosmic rays will have altered its surface chemistry. Impacts with dust grains will have eroded some areas, and perhaps added material in others. The constant cycle of heating and cooling as it passes near and far from various stars will have caused internal changes, perhaps creating new fractures or sealing old ones. This is rather like the ancient philosophical question of the ship of Theseus. If a ship has all its parts gradually replaced over time, is it still the same ship? If 3i Atlas returns changed by its journey, is it still the same comet that visited us before? There's no simple answer to this question, but contemplating it opens up wonderful avenues of thought about the nature of identity, change, and continuity in the cosmos. As we move deeper into our exploration of this cosmic mystery, let's consider the role that dark matter might play in the return of interstellar objects. Dark matter, that invisible substance that makes up most of the matter in the universe, doesn't interact with light or normal matter in ways we can easily detect. But it does have gravity, and lots of it. The galaxy is embedded in a vast halo of dark matter, invisible but influential, shaping the orbits of stars and potentially affecting the paths of interstellar wanderers like 3i Atlas. We don't fully understand dark matter yet. It remains one of the great mysteries of modern physics, but we know it's there, revealed by its gravitational effects on visible matter, and if 3i Atlas passes through regions of space where dark matter is particularly dense, these invisible clouds could alter its trajectory in ways we can't predict with our current understanding. Perhaps dark matter acts as a kind of cosmic memory foam, recording the passage of objects through its invisible bulk and occasionally redirecting them back toward regions they visited before. This is highly speculative, of course, but that's the beauty of contemplating cosmic mysteries as we drift towards sleep. We're free to wonder, to imagine, to consider possibilities that might seem outlandish in the harsh light of day, but feel perfectly reasonable in the gentle darkness of night. And who knows? Some of today's wild speculations might turn out to be tomorrow's scientific breakthroughs. The history of astronomy is full of ideas that seemed impossible until they were proven true. The gentle pull of sleep might be starting to tug at your consciousness now, and that's perfectly fine. Let your mind wander among the stars as your body relaxes deeper into rest. There's no need to hold on to any particular thought or follow any specific thread. Like 3i Atlas itself, let your thoughts follow their own trajectory through the cosmos of imagination, perhaps circling back to ideas you've already considered, perhaps venturing into new territory entirely. As we contemplate cosmic cycles and returns, it's worth considering how the concept of return appears throughout human culture and mythology. The eternal return is a concept that appears in many philosophical and religious traditions. The idea that existence repeats itself in cycles, that what has happened will happen again. The ancient Greeks had their concept of the great year, a vast cycle after which the cosmos would return to its starting configuration. Hindu and Buddhist cosmology speaks of kalpas and mahakalpas, immense cycles of creation and destruction spanning billions of years. Perhaps there's something deep in human consciousness that recognizes these patterns, that intuits the cyclical nature of existence, even without understanding the physics behind it. When we look at 3i Atlas and wonder about its possible return, we're tapping into this ancient wisdom, this recognition that the universe operates in circles and spirals rather than straight lines. Nothing is ever truly finished, nothing ever completely lost. Everything returns in one form or another, transformed by its journey, but still connected to its origins. The scientific understanding of orbital mechanics gives us a mathematical framework for understanding these returns. But the wonder and mystery remain intact. In fact, the more we learn about the precise mechanisms by which objects move through space, the more amazing it becomes that such beautiful, complex patterns can emerge from simple physical laws. The same force that causes an apple to fall from a tree orchestrates the dance of galaxies. The same conservation laws that govern collisions between billiard balls determine the fate of interstellar comets over billions of years. As we prepare to journey deeper into the implications of cosmic returns and cycles, to explore what the possible return of 3i Atlas might mean for our understanding of our place in the universe, let's take a moment to appreciate the profound privilege of being conscious, beings capable of contemplating these mysteries. Of all the matter in the universe, only a tiny fraction has organized itself into forms capable of awareness, of wonder, of asking questions about origins and destinies. We are the universe becoming aware of itself, and every time we ponder the journey of an interstellar comet, we're participating in that cosmic self-awareness. The story of 3i Atlas is far from over. In fact, it's barely begun. As our visitor continues its journey through interstellar space, it carries with it not just the physical materials of its composition, but also the memory of its encounter with our solar system. The gravitational perturbations it experienced here, the material it might have lost or gained, the subtle changes in its trajectory, all of these will influence its future path through the galaxy. And somewhere, encoded in those changes, is the story of its brief visit to our cosmic neighborhood, a story that will be carried forward through deep time until, perhaps, it finds its way back to us again. But that return, if it happens, is a story for the far future, for beings we cannot imagine living in a world we cannot envision. For now, in this precious present moment, we have the memory of its visit and the questions it raised. We have the data collected by our telescopes and the theories proposed by our scientists. Most importantly, we have the sense of wonder it inspired, the reminder that we are not alone in the cosmos, that messengers from other stars do occasionally grace us with their presence, and that the universe is far more interconnected than our everyday experience might suggest. As you continue to relax, perhaps feeling yourself beginning to drift like a comet through the peaceful darkness of approaching sleep, remember that you too are on a journey through space. The Earth carries you around the sun at tremendous speed. The sun carries Earth around the galaxy, and the galaxy itself moves through the cosmic web. You're a traveler on multiple scales simultaneously, participating in cycles within cycles, patterns within patterns. And just as 3i Atlas might one day return to our solar system, you return each night to the realm of sleep and dreams, only to wake again and continue your journey through consciousness and cosmos alike. The mathematics of orbital mechanics tells us that every trajectory through space is unique, determined by initial conditions and subsequent interactions. No two objects follow exactly the same path, and yet there are patterns, resonances, places where paths cross and recross. The universe seems to delight in creating both uniqueness and repetition, both novelty and return. 3i Atlas embodies this duality perfectly. A unique object following a unique path that might, through the beautiful complexity of cosmic motion, bring it back to us again in the fullness of time. Consider for a moment the sheer audacity of what we're contemplating. We're talking about an object that has travelled for billions of years, across distances so vast that light itself takes millennia to traverse them, possibly returning to a single star system among hundreds of billions in our galaxy alone. The odds seem impossible, and yet the universe specializes in making the impossible merely improbable, and the improbable, given enough time, inevitable. This is the kind of thinking that expands our consciousness, that reminds us that we live in a cosmos far stranger and more wonderful than our ancestors could have imagined. The story of 3i Atlas also reminds us of the importance of patience in understanding the universe. Our individual lives are so brief compared to cosmic timescales that we see only snapshots of processes that unfold over millions or billions of years. We're like mayflies trying to understand the seasons, glimpsing only a single day of what is actually a year-long cycle. But through science, through careful observation and mathematical modelling, we can extend our perception beyond the limits of our lifespan. We can imagine and calculate and predict events that will occur long after our sun has exhausted its fuel and Earth has become unrecognizable. This extension of consciousness through time is one of humanity's greatest achievements. When we talk about 3i Atlas possibly returning, we're exercising this uniquely human ability to think beyond our immediate temporal boundaries, to consider possibilities that exist on timescales that dwarf not just individual lives, but entire civilizations. It's both humbling and empowering. Humbling because it reminds us how brief our individual existence is, empowering because it shows us that through thought and imagination, we can transcend those limitations. As we prepare to delve even deeper into the mysteries of cosmic cycles and the ancient pathways that objects like 3i Atlas follow through space and time, let's carry with us this sense of expanded consciousness, this ability to think in deep time. The universe has been patient enough to wait billions of years to bring us this interstellar visitor. Surely we can be patient enough to contemplate its journey properly, to let our minds wander along the paths it has taken and might take again, to wonder without urgency about the messages it carries and the stories it could tell. The night is still young in cosmic terms, and our journey through these mysteries has only just begun. Like 3i Atlas itself, we have a long path ahead of us, full of wonders to discover and questions to ponder. Some of these questions might find answers as we explore further. Others might remain mysteries, and that's perfectly fine. In fact, it's more than fine. It's beautiful. A universe without mysteries would be a universe without wonder, and wonder is what makes consciousness worthwhile. So let's continue our journey, following the path of our interstellar visitor backward through time to understand where it came from and how it found its way to us. The cosmos has a way of keeping time that makes our human calendars seem almost quaint in comparison. Where we measure our lives in decades and our civilizations in millennia, the universe marks its passage in epochs that stretch across billions of years. And somewhere in that vast expanse of time, longer ago than our minds can truly grasp, the object we call 3i Atlas began its incredible journey toward us. To understand the possibility of its return, we must first journey backward, tracing its path through the eons, imagining the vast stretches of time and space it has traversed. Picture, if you will, the galaxy as it was billions of years ago. The Milky Way was younger then. its spiral arms perhaps wound differently, its stellar population consisting of different generations of stars than those we see today. Our own sun hadn't even begun to form yet. The cloud of gas and dust that would eventually collapse to create our solar system was still dispersed among the interstellar medium, waiting for some triggering event to begin the process of stellar birth. And somewhere in this younger galaxy, in a star system whose location we can only guess at, the 3-Ayas Atlas was taking shape. The birth of a comet is not a sudden event but a gradual accumulation, a slow gathering of materials in the cold outer reaches of a forming planetary system. It begins with tiny grains of dust, each no larger than a speck of smoke, drifting through the protoplanetary disk that surrounds a young star. These grains are made of various materials, silicates from the rocky components, ices of water and methane and carbon dioxide that can only remain solid in the cold depths far from the star's warmth. And mixed among them are organic molecules, complex carbon-based compounds that form naturally in the cold and radiation of space. These grains don't remain separate for long, cosmically speaking. Through a process called accretion, they begin to stick together. At first, it's just electrostatic forces and van der Waals interactions, the same weak forces that make dust cling to your furniture. But as clumps grow larger, gravity begins to play a role. A clump the size of a pebble has enough gravity to attract nearby dust grains. A boulder-sized object can pull in pebbles, and eventually mountain-sized bodies called planetesimals form, with enough gravity to significantly affect their surroundings. 3C Atlas likely formed from countless such interactions, growing from microscopic dust grains to the mountain-sized object we observed passing through our solar system. This process would have taken millions of years, a time during which the rest of its home system was also taking shape. Perhaps massive gas giants were forming closer to the star, their powerful gravity stirring up the orbital dynamics of the entire system. Perhaps terrestrial planets were assembling themselves from rocky planetesimals, colliding and merging in spectacular impacts that melted entire worlds. During this chaotic early period of planetary system formation, the object that would become 3I Atlas was just one of countless similar bodies, all orbiting their parent star in a vast cloud of comets that astronomers call the Oort cloud, named after the Dutch astronomer Jan Oort who first proposed its existence. Every star system likely has such a cloud, extending perhaps a light year or more from the central star, a vast reservoir of icy bodies preserved in deep freeze since the system's formation. Now, here's where our story takes its crucial turn. For most comets in these distant clouds, their fate is to remain there essentially forever, orbiting so far from their star that they're barely bound by its gravity, preserved in the cold and darkness like seeds in a cosmic vault. Occasionally, gravitational perturbations might send one falling toward the inner system, where it becomes a visible comet with its characteristic tail, but most will never experience this. They'll simply orbit in the darkness until their star dies, and even then, many will remain bound to the stellar remnant. But 3 Atlas experienced something different, something that would set it on a journey across the galaxy. The exact mechanism remains a mystery. There are several possibilities, each fascinating in its own way. Perhaps it was a close encounter with a massive planet in its home system, a gravitational slingshot that accelerated it beyond escape velocity. Imagine a gas giant many times the mass of Jupiter, its gravity reaching out across millions of miles to grab passing comets and fling them in new directions. Most would be sent into different orbits still bound to the star, but occasionally one would receive just the right boost to break free entirely. Or perhaps the liberation of 3 Atlas was caused by something external to its home system. Stars don't exist in isolation. They have neighbours, and occasionally these neighbours pass close enough to affect each other's comet clouds. When a star passes within a light year or so of another star, close by cosmic standards though still vastly farther than the distance from Earth to the Sun, its gravity can disturb the orbits of comets in the outer cloud. Most disturbances are minor, but some comets can be pulled free entirely, stolen from one star or ejected into interstellar space. There's something poetic about this process, isn't it? A comet that spent millions of years forming, gathering its materials grain by grain, suddenly set free by a chance encounter to wander the galaxy. It's like a child leaving home, but on a scale that dwarfs human experience. And once free, 3 Atlas began a journey that would last billions of years before bringing it to our doorstep. Let's try to imagine what that journey was like, though of course we must acknowledge that a comet has no consciousness, no awareness of the passing eons. For 3 Atlas, the billions of years of interstellar travel would pass in absolute darkness and cold. The temperature of interstellar space is only a few degrees above absolute zero, cold enough that even the molecules in the comet would barely vibrate. Any gases that might try to escape would immediately freeze back onto the surface. The comet would become a perfectly preserved time capsule, locked in a state of suspended animation. But while the comet itself remained largely unchanged, the galaxy around it was evolving dramatically. As 3I Atlas drifted through space at speeds of perhaps tens of kilometers per second, fast by human standards, but a crawl compared to the speed of light, entire stellar generations were being born and dying around it. Massive stars, those cosmic furnaces that burn through their fuel in just millions of years, would have gone through their entire life cycles hundreds or thousands of times during 3I Atlas's journey. Each stellar death would have enriched the interstellar medium with heavy elements, gradually changing the chemical composition of the galaxy. The path 3 Atlas followed through the galaxy wasn't a straight line. Even in the supposed emptiness of interstellar space, gravity is always at work. Every star the comet passed, even at distances of light years, exerted a tiny gravitational pull that slightly altered its trajectory. Over millions and billions of years, these tiny course corrections added up, turning what might have started as a straight path into a complex winding journey through the galaxy. Think of it like a leaf falling from a tree on a perfectly calm day. The leaf doesn't fall straight down. It flutters and spirals, affected by the tiniest air currents, by its own shape and weight distribution, by 1,000 factors too subtle to perceive. Now imagine that leaf falling for billions of years through a medium where the air currents are gravitational fields extending across light years, where the forces acting on it are so weak they could never be felt but so persistent they never stop. That's something like the journey 3I Atlas has taken through the galaxy. During its journey, 3I Atlas would have passed through various environments within the galaxy. Sometimes it would have travelled through relatively dense regions where stars are closer together, perhaps the outskirts of star clusters, where hundreds or thousands of stars occupy a volume of space just a few light years across. The combined gravity of these stellar assemblies would have bent its path more dramatically, perhaps sending it off in an entirely new direction. At other times, 3I Atlas would have traversed the vast voids between spiral arms, regions where stars are few and far between, where it might travel for millions of years without passing within a light year of another star. In these cosmic deserts, its path would have been straighter, its motion less perturbed, carrying it across vast distances like a ship sailing through calm seas. And all the while, the galaxy itself was rotating, carrying 3 Atlas along in its grand spiral dance. The comet's motion through space was never just its own. It was always a combination of its initial ejection velocity, the gravitational perturbations it experienced, and the overall rotation of the galaxy itself. It's like trying to walk across a moving carousel while also being pulled and pushed by invisible hands. The resulting path is complex beyond easy prediction. One of the most fascinating aspects of 3I Atlas's journey is that it has likely passed through regions of space we will never see, never explore, never know anything about except through messengers like this comet. It has been to places that no probe from Earth will reach for millions of years, if ever. In its ice and rock, it might carry trace materials picked up during its journey, individual atoms or molecules captured from the interstellar medium, cosmic dust grains that stuck to its surface, perhaps even microscopic impacts from other interstellar wanderers. Each of these additions would be incredibly rare. The density of matter in interstellar space is so low that 3I Atlas might travel for thousands of years between encounters with even a single atom. But over billions of years, even these rare events accumulate. The surface of the comet becomes a kind of collection plate, gathering samples from across the galaxy. If we could read this record perfectly, if we could identify and analyze every foreign atom on 3I Atlas's surface, we would have a partial map of its journey through the galaxy. Consider the cosmic radiation that has bombarded 3I Atlas throughout its journey. Cosmic rays, high-energy particles accelerated by supernovae, stellar winds, and other energetic events, have been striking the comet constantly for billions of years. These impacts cause nuclear reactions in the comet's surface layers, creating isotopes that wouldn't form under normal conditions. The ratios of these isotopes can tell us about the radiation environment the comet has experienced, which in turn tells us something about the regions of space it has traveled through. Some of these cosmic ray interactions produce radioactive isotopes with half-lives of millions of years. By measuring the abundance of these isotopes, scientists can estimate how long the comet has been exposed to cosmic rays, essentially carbon dating its journey through space. It's like the comet carries its own clock, marking the passage of eons in the slow decay of unstable atoms. The organic molecules within 3I Atlas have their own stories to tell about this long journey. When cosmic rays strike organic compounds, they can break chemical bonds and create new molecules. Over billions of years, this process can produce a complex chemistry that wouldn't occur under any other conditions. Some scientists speculate that interstellar comets might be factories for prebiotic molecules, creating the chemical precursors to life through the slow, patient chemistry of deep space and deep time. Imagine the comet passing through a stellar nursery, one of those vast clouds of gas and dust where new stars are being born. The Orion Nebula, visible to us as a fuzzy patch in Orion's sword, is one such region we can see from Earth. These nurseries are places of both creation and destruction, where the radiation from young hot stars illuminates the surrounding gas, creating spectacular nebulae, while also evaporating and destroying smaller bodies that venture too close. If 3I Atlas passed through such a region, it would have been bathed in intense ultraviolet radiation from the young stars. This radiation would have altered its surface chemistry, perhaps creating a hardened crust of complex organic polymers. It might have accumulated a coating of dust and gas from the nebula, adding new materials to its composition. And if it passed close enough to feel the stellar winds from these young stars, it might have experienced a brief warming, a temporary awakening from its frozen slumber, before returning to the cold darkness of interstellar space. There's also the possibility that 3I Atlas has had close encounters with other stellar systems during its journey. Not captured, but passing through the outer regions of other comet clouds, perhaps even diving through the planetary region of alien solar systems. Each such encounter would be a cosmic dice roll. Most of the time the comet would pass through without incident, the spaces between planets being vast. But there's always the chance of a more dramatic interaction. What if 3I Atlas passed within the orbit of an alien world's moon system? The gravitational perturbations would alter its trajectory, of course, but more intriguingly, it might have been observed by whatever beings, if any, inhabited that system. Just as we detected and studied 3I Atlas during its passage through our solar system, perhaps other civilizations have done the same. Our interstellar visitor might be recorded in the astronomical archives of worlds we don't even know exist, a shared point of reference between civilizations that will never meet. This raises profound questions about the role of interstellar comets as unintentional messengers between star systems. Every comet carries information about its origin, the isotopic ratios that tell of the stellar nursery where its materials were forged, the chemical composition that speaks to the conditions in its home system, the organic molecules that hint at the chemistry possible in that distant place. When 3D Atlas passed through our solar system, it brought all of this information to us, a scientific treasure trove delivered across billions of years and countless light years. And we're not just passive recipients of these messages. As 3D Atlas passed through our solar system, it was altered by the experience. The sun's heat caused outgassing that changed its mass distribution. The solar wind and our sun's magnetic field affected its surface. The gravitational pulls of our planets altered its trajectory. When 3I Atlas continues on to its next stellar encounter, millions or billions of years from now, it will carry with it subtle evidence of its visit to our solar system. In this way, interstellar comets become like cosmic bulletin boards, accumulating messages from each system they visit. The messages are written in the language of chemistry and physics rather than words, but they're messages nonetheless. And if such an object were to return to a system it had visited before, it would bring with it a record of everywhere it had been in between, a travelogue written in ice and stone. The timescales involved in these journeys challenge our perception of what constitutes an event or a process. From our human perspective, the passage of 3I Atlas through our solar system was a brief event, lasting perhaps a year or two from detection to departure. But from a cosmic perspective, this was just an instant in a journey spanning billions of years. The comet's orbit, if we can even call it an orbit when it's not bound to any particular star, operates on timescales that make the entire history of human civilization look like a single frame in a cosmic movie. Let me paint you a picture of the galaxy as 3I Atlas has experienced it. When its journey began, the Milky Way looked noticeably different. The spiral arms were in different positions relative to the galactic center. Some of the star clusters we see today didn't exist yet, while others that were prominent then have since dispersed. The supermassive black hole at our galaxy's center has consumed millions of solar masses of material in the intervening time, occasionally flaring with tremendous brightness as particularly large meals fell into its gravitational embrace. During 3 Atlas's journey, our galaxy has completed perhaps a dozen rotations. From the comet's perspective, if it could perceive such things, the galaxy would appear to be turning beneath it like a vast, slow whirlpool of stars. Stellar streams, the remnants of smaller galaxies torn apart by the Milky Way's gravity, have been created and dispersed. Globular clusters have orbited the galaxy dozens of times, their paths gradually evolving due to gravitational interactions. And through all of this change and motion, 3I Atlas has continued its journey, a constant in a universe of variables. Its path has been affected by all of these changes, of course. The redistribution of mass in the galaxy affects the gravitational field through which it travels. But the comet itself has remained essentially unchanged, a frozen artifact from an earlier epoch carrying its primordial composition through an evolving cosmos. This preservation is one of the most valuable aspects of interstellar comets from a scientific perspective. While stars evolve and die, while planets change and potentially develop life, while galaxies collide and merge, these small frozen bodies remain largely unchanged. They're like cosmic fossils preserving information about conditions billions of years ago. When we study 3I Atlas, we're not just learning about another star system, we're learning about that star system as it was billions of years ago, seeing a snapshot from the galaxy's past. The organic chemistry preserved in 3I Atlas is particularly fascinating in this context. We know that organic molecules can form in space through various processes, in the atmospheres of dying stars, in the cold clouds between stars, on the surfaces of dust grains exposed to radiation. But the specific mix of organic compounds in any particular comet depends on the conditions where it formed and the processing it has experienced since. 3I Atlas's organic inventory is like a chemical fingerprint, unique to its particular history. Some of these organic molecules might be types we've never seen before. The conditions in 3I Atlas's home system might have been just different enough from our own to produce novel chemistry. Perhaps the star it formed around was richer or poorer in certain elements. Perhaps the temperature and pressure conditions in the protoplanetary disk were unusual. Perhaps the radiation environment was different. All of these factors could lead to the formation of organic molecules that don't exist in our solar system. And then there's the processing that occurred during the billions of years of interstellar travel. Cosmic rays breaking and reforming molecular bonds. The slow, patient chemistry that occurs even at temperatures near absolute zero. The occasional warming if the comet passed close to a star. Each of these processes would have altered the chemical inventory, potentially creating new compounds or destroying others. By the time 3I Atlas reached us, its chemistry was the product of billions of years of cosmic processing. As you lie there in the darkness, perhaps feeling the weight of billions of years settling over you like a comfortable blanket, consider how 3I Atlas connects us to the deep history of the galaxy. Every atom in the comet, every molecule, has a story that stretches back to the Big Bang itself. The hydrogen in its water ice formed in the first moments after the universe began. The heavier elements were forged in the nuclear furnaces of stars that lived and died before our sun was born. And the complex molecules represent billions of years of chemical evolution, a testament to the universe's ability to create complexity from simplicity. The journey of 3I Atlas also illustrates a profound truth about the nature of space and time. We often think of space as empty and time as uniform, but the comet's journey shows us that both are rich with structure and meaning. Space is filled with invisible influences, gravitational fields, magnetic fields, streams of particles, waves of radiation. And time is marked by events and processes occurring on every possible scale, from the vibration of atoms to the rotation of galaxies. As 3I Atlas travelled through the galaxy, it was simultaneously participating in processes occurring on vastly different timescales. The atomic vibrations in its ice happened trillions of times per second. Chemical reactions on its surface might take years or centuries. Its passage through interstellar clouds might last millennia. Its journey between stars spans millions of years. And its complete traverse of the galaxy takes billions of years. All of these timescales coexist, nested within each other like Russian dolls, each important in its own way. This multi-scale nature of time is something we rarely appreciate in our daily lives, where we are concerned mainly with timescales from seconds to years. But when we contemplate objects like 3I Atlas, we're forced to expand our temporal horizons, to think in what Timothy Morton calls hyper-objects, things that exist on scales so vast that we can only perceive parts of them at any given time. The full journey of 3I Atlas is such a hyper-object, too large in both space and time for us to grasp in its entirety, yet undeniably real and affecting our world in measurable ways. As we prepare to explore how 3I Atlas might find its way back to our solar system, how the mathematics of orbital mechanics might conspire to create a cosmic return, it's worth pausing to appreciate the sheer improbability of its first visit. Out of all the possible paths through the galaxy, out of all the directions it could have travelled after being ejected from its home system, it happened to pass through our tiny corner of space at precisely the time when we had developed the technology to detect and study it. This wasn't planned, of course. There was no intention behind it, no cosmic purpose guiding 3I Atlas to us. It was simply the result of the laws of physics playing out over billions of years, the inevitable consequence of initial conditions we'll never fully know. And yet, the result feels almost miraculous. A messenger from another star system arriving just as we became capable of reading its message. Some might see this as evidence of cosmic significance, others as pure coincidence. But perhaps the truth is somewhere in between. Perhaps the universe is structured in such a way that these kinds of encounters, while rare, are inevitable given enough time and space. Perhaps the same laws that make interstellar comets possible also make their eventual detection by curious civilizations likely. Perhaps we're participating in a cosmic pattern that repeats throughout the galaxy, with civilizations regularly receiving and studying visitors from other star systems. The path that brought 3 Atlas to us was shaped by countless influences over billions of years. Every star it passed, every cloud of interstellar gas it traversed, every fluctuation in the galactic gravitational field, all of these factors combined to deliver it to our doorstep at exactly the right moment. It's a reminder that in the universe, everything is connected to everything else, even if the connections are subtle and play out over incomprehensible timescales. And now, as 3 Atlas continues its journey away from our solar system, those same forces are shaping its future path. The gravitational boost it received from our Sun has altered its trajectory through the galaxy. Its encounter with our solar system has become part of its story, encoded in its orbital parameters, and somewhere in the complex mathematics that govern its motion, there might be the seeds of a return, a closing of the circle that would bring it back to our neighborhood in the far future. But to understand how such a return might be possible, we need to delve into the beautiful, complex mathematics that govern motion on galactic scales. We need to explore how orbits work not just around stars but around the galaxy itself, how stellar encounters can redirect trajectories, how the patient pull of gravity over millions of years can turn departure into return. The universe, it turns out, has a memory encoded in the paths objects take through space, and sometimes, just sometimes, that memory brings wanderers home. The mathematics that govern the motion of objects through space are simultaneously simple and impossibly complex. At their heart lies Newton's law of universal gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It's an equation you could write on a napkin. Yet from this simplicity emerges the incredible complexity of cosmic motion, the dance that might one day bring 3 Atlas back to our solar system. When we think about the possibility of 3 Atlas returning, we're really asking whether the path it's following through space could ever curve back upon itself, creating a closed loop that intersects with our solar system's future position. To understand how this might happen, we need to think about motion on multiple scales simultaneously. The comet's motion relative to our sun's motion through the galaxy, and the galaxy's own evolution over time. Let's start with something familiar and work our way up to the cosmic scale. When you throw a ball on Earth, it follows a parabolic path, rising and then falling back to the ground. If you could throw it hard enough, at about 11 kilometers per second, it would escape Earth's gravity entirely and never fall back. This is called escape velocity, and it's different for every celestial body depending on its mass and size. The escape velocity from our solar system, starting from Earth's distance from the Sun, is about 42 kilometers per second. When 3I Atlas passed through our solar system, it was travelling faster than this escape velocity. That's how we knew it was an interstellar object. It had too much kinetic energy to be captured by our Sun's gravity. But here's where things get interesting. Escape velocity is always defined relative to a specific gravitational field. 3I Atlas has escaped our Sun's gravity. Yes, but it hasn't escaped the galaxy's gravity. It's still bound to the Milky Way, still participating in the grand rotation around the galactic centre. Think of it this way. Imagine you're on a massive carousel and you throw a ball outward. From your perspective on the carousel, the ball flies away in a straight line. But from the perspective of someone standing still beside the carousel, the ball is following a curved path, influenced both by your throw and by the rotation of the carousel itself. Our solar system is like a horse on the galactic carousel, and 3I Atlas is like a ball we've observed flying past us. Its path through space is a combination of its own motion and the rotation of the entire galaxy. The Milky Way rotates differentially, meaning that stars closer to the centre complete their orbits faster than those farther out. Our Sun, located about 26,000 light-years from the galactic centre, takes approximately 230 million years to complete one orbit. This is sometimes called a cosmic year, or a galactic year. In the time since 3i Atlas was ejected from its home system billions of years ago, it has completed multiple orbits around the galaxy, its path slowly evolving with each circuit. Now, here's where the mathematics becomes beautiful and strange. In a simple two-body system, say, just our Sun and 3i Atlas, the comet would follow a hyperbolic trajectory, approaching from infinity and returning to infinity, never to return. But the galaxy isn't a two-body system. It contains hundreds of billions of stars, vast clouds of gas and dust, and an even vaster amount of dark matter. Each of these components contributes to the overall gravitational field through which 3i Atlas travels. The path of any object through this complex gravitational field is what mathematicians call a chaotic trajectory. This doesn't mean it's random, the path is completely deterministic, governed by the laws of physics. But it's chaotic in the technical sense that tiny changes in initial conditions can lead to vastly different outcomes over time. A difference of just a few meters per second in velocity, or a few astronomical units in position, could determine whether 3i Atlas returns to our neighborhood in 1 billion years or never comes close again. This sensitive dependence on initial conditions is what makes predicting the long-term future of 3i Atlas's orbit essentially impossible with our current observations. We know its trajectory well enough to say where it will be in the next few thousand years, but beyond that, uncertainty grows exponentially. It's like trying to predict weather patterns years in advance. The underlying physics is understood, but the system is too complex and our measurements too imprecise for long-term prediction. But even if we can't predict the specific path 3i Atlas will take, we can understand the types of paths that are possible, and this is where things get really interesting. In the complex gravitational field of the galaxy, there exist what mathematicians call invariant manifolds, invisible tubes or channels in space along which objects tend to flow. These are like cosmic highways, paths of least resistance through the gravitational landscape. These manifolds connect different regions of the galaxy in non-obvious ways. An object following one of these paths might travel outward from the inner galaxy, loop around through the halo, and return to the inner regions millions of years later. It's a bit like ocean currents. Water that starts in one part of the ocean can follow currents that carry it around the world and eventually back to where it started, though the specific molecules of water are never quite in the same place twice. For 3i Atlas to return to our solar system, it would need to follow one of these manifolds that happens to intersect with our Sun's future position. This isn't as unlikely as it might seem. The galaxy is crisscrossed with these gravitational channels, and objects are constantly flowing along them. Some astronomers estimate that our solar system is visited by an interstellar object like 3i Atlas every few years. We just haven't had the technology to detect them until recently. But there's another mechanism that could bring 3i Atlas back, one that involves the stellar encounters I mentioned earlier. As our comet travels through the galaxy, it occasionally passes relatively close to other stars. Each encounter changes its velocity slightly, bending its path through space. Over millions of years and thousands of encounters, these small deflections can add up to major trajectory changes. There's a beautiful mathematical framework for understanding these encounters, called the three-body problem. When you have three gravitational bodies, say 3i Atlas, our Sun, and another star, their interactions become incredibly complex. There's no general closed-form solution to the three-body problem, meaning we can't write down a simple equation that tells us exactly what will happen. Instead, we have to use numerical simulations, calculating the positions and velocities moment by moment. These three-body interactions can produce what are called resonances, special configurations where the orbital periods of the bodies are related by simple ratios. For example, if 3i Atlas's orbit around the galaxy became synchronized with our Sun's orbit in a 2-3 resonance, it would complete 2 orbits for every 3 orbits our Sun completes. Resonances can be stable, locking objects into repeating patterns that bring them back to the same relative positions over and over again. The galaxy is full of these resonances. They're what create the spiral arms we see in galaxies like ours, density waves that rotate at specific rates, creating traffic jams of stars and gas. If 3i Atlas becomes trapped in one of these resonances, it could be carried along with the spiral pattern, its orbit stabilizing into a predictable pattern that might, over many galactic rotations, bring it back to our neighborhood. There's also the fascinating possibility of what astronomers call a horseshoe orbit. In this type of orbit, an object appears to travel in a horseshoe-shaped path relative to a larger body. From the perspective of the larger body, in this case, perhaps our Sun, the smaller object seems to approach, reverse direction, and retreat, only to approach again from the other direction millions of years later. It's not actually reversing, of course. It's following an orbit that, due to the relative motion of the two bodies, creates this illusion. Could 3i Atlas be in the early stages of such an orbit relative to our Sun? It's unlikely, but not impossible. The initial conditions would have to be just right, the velocities and positions aligned in a very specific way. But given the vast number of interstellar objects in the galaxy, some of them must be following these exotic orbits, and if 3i Atlas is one of them, it could return to our solar system not once but repeatedly, visiting us every few million or billion years like a cosmic pendulum. The role of dark matter in shaping these orbits adds another layer of complexity and possibility. Dark matter doesn't interact with normal matter except through gravity, but its gravitational effects are profound. The Milky Way is embedded in a vast halo of dark matter that extends far beyond the visible disk of stars. This halo isn't uniform. It has structure, clumps, and streams that create variations in the gravitational field. As 3i Atlas travels through this dark matter halo, it experiences gravitational forces we can't directly observe. These forces could bend its trajectory in ways our current models don't fully account for. Perhaps dark matter concentrations act as gravitational lenses, focusing the paths of interstellar objects in ways that increase the likelihood of return visits. Perhaps the dark matter halo has its own system of gravitational manifolds, invisible highways that guide objects on billion-year journeys through the galaxy. Recent simulations of galaxy formation and evolution have revealed that dark matter halos often contain streams and shells, the remnants of smaller galaxies that have been absorbed by the Milky Way over cosmic time. These structures can persist for billions of years, creating permanent features in the gravitational landscape. If 3i Atlas enters one of these streams, it could be carried along like a leaf in a river, its path determined by the flow of dark matter, rather than the distribution of visible stars. The mathematical beauty of orbital mechanics extends to something called the Jacobi integral, a conserved quantity in the circular restricted three-body problem. This integral defines surfaces in space that an object cannot cross. They're like invisible barriers created by the combination of gravity and rotation. For 3i Atlas, traveling through the rotating galaxy, these Jacobi surfaces create a complex topology of allowed and forbidden regions. Imagine the galaxy as a landscape of hills and valleys, but in multiple dimensions. 3i Atlas can only travel through valleys below a certain altitude determined by its energy. As it moves through this landscape, it might find itself channeled along valley floors, unable to climb over the surrounding peaks. These valleys might wind through space in complex patterns, but they're not infinite. Eventually, they must either close on themselves or connect to other valleys. If 3i Atlas is following a valley that closes on itself, it must eventually return to regions it has visited before. The concept of phase space adds another dimension to our understanding of possible returns. Phase space is a mathematical space where each point represents a possible state of a system, in this case, the position and velocity of 3i Atlas. The path of the comet through phase space is called its trajectory or orbit. In certain dynamical systems, these orbits can be quasi-periodic, meaning they don't exactly repeat, but come arbitrarily close to previous states over time. A quasi-periodic orbit in phase space could bring 3i Atlas back to almost the same position and velocity it had, when it passed through our solar system, but billions of years later. It wouldn't be an exact return. The galaxy will have rotated many times, stars will have moved, our sun itself will be in a different location. But the relative configuration might be similar enough that 3i Atlas passes through our solar system again, approaching from a slightly different angle perhaps, but recognizable as the same object. The CAM theorem, named after Kolmogorov, Arnold and Moser, tells us something profound about the stability of orbits in complex systems. It says that even in chaotic systems, there exist islands of stability, regions where orbits remain regular and predictable over long timescales. These CAM tori, as they're called, are like safe harbours in a sea of chaos. If 3i Atlas's orbit lies on or near one of these tories, its long-term behaviour might be more predictable than the general chaotic nature of the galaxy would suggest. Let me paint you a picture of how a return might actually happen, step by step, over millions of years. After leaving our solar system, 3i Atlas continues outward, its path gradually curving due to the galaxy's rotation. Perhaps a million years from now, it passes within a light year of another star, receiving a gravitational nudge that alters its trajectory slightly. This new path carries it into a denser region of the galaxy, where stellar encounters are more frequent. Over the next 10 million years, dozens of these encounters gradually turn its outward motion into motion along the galactic disk. It's now travelling roughly parallel to our Sun's orbit, but at a different radius and speed. The differential rotation of the galaxy means it's either catching up to our Sun or falling behind, depending on whether it's closer or farther from the galactic centre. 100 million years pass. 3i Atlas has encountered a giant molecular cloud, a vast region of dense gas where new stars are forming. The gravitational field of this cloud, containing the mass of millions of suns, significantly alters the comet's orbit. It emerges on a new trajectory that's slowly converging with the orbit our Sun will follow in the future. After 1 billion years, 3i Atlas has completed several orbits of the galaxy, its path evolving with each circuit. It's entered a mean motion resonance with a massive star cluster, which stabilizes its orbit and reduces the chaotic variations. The resonance slowly drives the comet's orbit toward a configuration that will intersect with our Sun's future path. 2 billion years have passed. Our Sun has aged noticeably, growing slightly brighter and larger. Earth, if it still exists, has changed dramatically. And 3 Atlas, following its patient path through the galaxy, is approaching the region of space our solar system will occupy in just a few million more years. The timing has to be perfect, a cosmic coincidence measured in millions of years rather than seconds. And then, one day in the impossibly distant future, astronomers, perhaps not human, perhaps not even biological, detect a familiar signature, an object approaching on a hyperbolic trajectory, moving too fast to be from our solar system. But when they analyze its composition, compare its isotopic ratios to ancient records preserved through eons of technological and biological change, they realize this isn't a new visitor, it's 3i Atlas, returned after billions of years of wandering. The mathematics tell us this is possible, unlikely perhaps, but possible. In the vast phase space of possible orbits through the galaxy, there exist paths that loop back on themselves, that return to neighbourhoods they've visited before, and given the vast timescales available, even unlikely events become possible, even possible events become probable, and probable events become certain. But the mathematics also tell us something else, that prediction and certainty are different things. We can know that returns are possible without being able to predict specific returns. The chaotic nature of the galaxy means that tiny uncertainties in our current measurements of 3i Atlas's trajectory balloon into vast uncertainties over cosmic timescales. We're left with statistical statements rather than definite predictions. There's perhaps a 1 in a million chance of return in the next billion years, 1 in 1,000 in the next 10 billion. These probabilities might seem discouragingly small, But remember that the galaxy contains billions of interstellar objects like 3i Atlas. If each has a 1 in a million chance of returning to a system it's visited before, then thousands of such returns are happening throughout the galaxy. We're not asking whether this specific comet will return to our specific solar system. We're asking whether the universe permits such returns at all. And the answer, written in the elegant language of orbital mechanics and celestial dynamics, is yes. The mathematics of return also connect to deeper principles in physics. The Poincaré recurrence theorem tells us that in certain systems, any state must recur to arbitrary accuracy given enough time. While the galaxy isn't quite the type of closed system the theorem requires, it suggests a general principle that in bounded systems with conserved quantities, returns are not just possible but inevitable given enough time. There's also the anthropic principle to consider. We observe 3i Atlas because we happen to exist at a time when it passed through our solar system. But if interstellar objects regularly return to systems they've visited before, then the fact that we observe this one might not be such a coincidence. Perhaps civilizations typically arise during periods when their systems are receiving multiple visits from interstellar objects, bringing water and organic molecules that seed life and evolution. As you drift deeper into contemplation of these mathematical possibilities, feeling perhaps the gentle pull of sleep beginning to assert itself like gravity on a comet, consider how the mathematics of orbital motion connect to the larger patterns of existence. Everything in the universe follows trajectories through various kinds of spaces. Physical space, certainly, but also chemical space, biological space, even conscious space. And in all of these spaces the same principles apply. Conservation laws create constraints, interactions create deflections, and given enough time, paths can curve back toward their origins. The specific mathematics governing 3i Atlas's motion through the galaxy are just one example of a universal principle, that the universe has a kind of memory encoded in the trajectories of objects through space and time. Every gravitational interaction leaves its mark, every encounter changes the future path, and the sum of all these influences creates the complex, beautiful, sometimes returning orbits we observe. As we prepare to explore what messages 3i Atlas might carry in its ice and stone, what information about distant places and times might be encoded in its chemical composition, remember that the mathematics we've been discussing aren't just abstract concepts. They're the universe's way of keeping track of everything, of ensuring that information is preserved even as it's transformed, that connections persist even across billions of years and billions of miles. The possibility of 3i Atlas's return isn't just about one comet coming back to our solar system. It's about the deeper truth that in a universe governed by mathematical laws, nothing is ever truly lost, nothing ever completely disconnected. The same forces that might bring 3i Atlas back to us connect us to every star in the galaxy, every galaxy in the universe. We're all following our trajectories through space and time, and sometimes through the beautiful mathematics of celestial mechanics. Those trajectories bring us back to places we've been before, changed by our journeys but still connected to our origins. The universe has a peculiar way of preserving information, encoding messages in the most unlikely of places, and perhaps nowhere is this more evident than in the frozen heart of an interstellar comet like 3i Atlas. As you settle deeper into the peaceful darkness, letting your mind wander through the cosmos, consider what secrets might be locked within those ancient ices. What stories are written in the molecular structure of this celestial wanderer? Every comet is a library, a repository of information about the time and place of its formation, and 3i Atlas is a library from another star system entirely, its volumes written in a chemical language that we're only just beginning to learn how to read. When we look at a comet, what we're really seeing is a time capsule that has been sealed since the birth of its parent star system. The ice and rock that make up 3i Atlas formed billions of years ago, from the same collapsing cloud of gas and dust that created its home star. As that primordial cloud collapsed, it carried with it the chemical signatures of its own history. the particular mix of elements created by previous generations of stars, the isotopic ratios that tell of the nuclear processes that forged those elements, the organic molecules that formed in the cold darkness of interstellar space. All of this information was locked into the comet's ice as it formed, preserved like insects in amber, waiting billions of years for someone to discover and decode it. The water ice that makes up much of 3I Atlas is itself a messenger from across the cosmos. Water is one of the most common molecules in the universe, formed wherever hydrogen and oxygen come together under the right conditions, but not all water is the same. The ratio of heavy water to regular water, molecules where one or both hydrogen atoms are replaced by deuterium, hydrogen's heavier isotope, varies depending on where and how the water formed. In our solar system, we've mapped these ratios across different bodies, finding that Earth's water has a particular signature, while comets from our Oort cloud have a slightly different one, and asteroids have yet another. When scientists analysed the water vapour streaming off 3I Atlas as it warmed in our sun's heat, they found ratios that didn't quite match anything in our solar system. It was close, suggesting that the basic processes of water formation are similar throughout the galaxy, but different enough to confirm its alien origin. These subtle differences are like an accent in a familiar language, telling us that while the words might be the same, the speaker comes from somewhere far away. The deuterium to hydrogen ratio in 3I Atlas's water tells us about the temperature and density of the nebula where it formed, the intensity of radiation from its parent star, perhaps even the presence of nearby stellar nurseries that enriched its birth cloud with heavy elements. But water is just the beginning of the story. Frozen within 3I Atlas as dozens, perhaps hundreds of different molecules, each carrying its own piece of information about conditions in that distant star system. Carbon dioxide, methane, ammonia, formaldehyde. These simple molecules are the building blocks from which more complex chemistry emerges. Their relative abundances tell us about the temperature gradient in the protoplanetary disk where 3I Atlas formed, about which molecules could condense into ice at different distances from the star, about the chemical processes that were occurring as the comet assembled itself from smaller particles. The noble gases trapped in 3 Atlas's ice are particularly valuable messengers. Argon, neon, xenon. These elements don't react chemically with other substances, which means they preserve information about their origins without modification. The ratios of different isotopes of these gases can tell us about the nucleosynthetic processes that created them, about whether they came from massive stars that exploded as supernovae, or from smaller stars that shed their outer layers more gently. Each star produces a slightly different mix of isotopes depending on its mass, composition, and life history, so the noble gases in 3I Atlas carry a fingerprint of the specific stars that enriched its birth nebula. Perhaps most intriguingly, 3I Atlas contains organic molecules, carbon-based compounds that in our own solar system are associated with the chemistry of life. Not life itself, to be clear, but the complex carbon chemistry that makes life as we know it possible. Spectroscopic observations detected hints of various organic compounds in the comet's coma, molecules with names like methanol, formaldehyde, and hydrogen cyanide. These aren't signs of biology, but rather the products of chemistry that occurs naturally in the cold, radiation-bathed environment of space. The specific mix of organic molecules in 3I Atlas tells us about the chemical processes that were occurring in its home system. Different conditions, temperature, radiation levels, the presence of catalytic dust grains, favour the formation of different organic compounds. It's like each star system has its own chemical recipe, its own way of cooking up organic molecules from the basic ingredients of carbon, hydrogen, oxygen, and nitrogen. By analysing the organic inventory of 3I Atlas, we're essentially reading that recipe, learning about chemical conditions in a place we'll never be able to visit directly. Some of these organic molecules might be types we've never encountered before. The vast majority of possible organic compounds have never been synthesized on Earth or detected in our solar system. They exist as theoretical possibilities, molecular structures that could form under the right conditions but haven't in our corner of the universe. 3i Atlas, coming from a different chemical environment, might carry some of these exotic molecules, expanding our understanding of what's chemically possible in the cosmos. Consider the implications of this for astrobiology, the study of life in the universe. We know that life on Earth is based on a relatively small set of organic molecules, amino acids that form proteins, nucleotides that form DNA and RNA, lipids that form cell membranes. But are these the only molecules capable of supporting life? Or might life elsewhere be based on a completely different chemical foundation? The organic molecules in 3i Atlas give us a glimpse of the chemical diversity that exists in other star systems, hint at the vast range of possible biochemistries that might exist in the universe. The mineral grains embedded in 3i Atlas's ice tell their own stories. These tiny particles, some no larger than smoke particles, others the size of sand grains, formed under specific conditions that left their mark on their crystal structure and composition. Some might be pre-solar grains, particles that formed in the atmosphere of dying stars and were incorporated into the nebula that gave birth to 3 Atlas's home system. These grains are older than any star currently shining, carrying information from the previous generation of stellar evolution. The crystal structure of these grains can tell us about the temperature and pressure conditions under which they formed. Some minerals only crystallize under very specific conditions, high temperatures near a forming star, or the extreme cold of the outer solar system, or the shock waves from stellar explosions. By identifying these minerals in 3i Atlas, we can reconstruct the environment of its formation, building a picture of what its home system was like billions of years ago. It's like being a cosmic archaeologist, reconstructing an entire civilization from a few pottery shards, except our shards are mineral grains, and our civilization is an entire star system. The surface of 3i Atlas has been modified by billions of years of exposure to cosmic rays, creating what scientists call a radiation mantle. This processed surface layer is like a diary of the comet's journey through interstellar space. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, strike the surface and cause nuclear reactions, creating new isotopes and breaking apart molecules. The depth of this radiation mantle, the specific isotopes it contains, the degree of molecular breakdown, all of these factors tell us how long 3i Atlas has been traveling through space and what kinds of radiation environments it has experienced. Some of the isotopes created by cosmic ray bombardment are radioactive with half-lives of millions of years. By measuring the abundance of these isotopes and their decay products, scientists can estimate when 3i Atlas was ejected from its home system, essentially carbon dating its interstellar journey. It's remarkable to think that we can determine to within a few million years when a comet from another star system began its journey toward us. The universe provides its own clocks, written in the slow decay of unstable atoms, and 3i Atlas carries several of these clocks within its ice and rock. The coma and tail that 3i Atlas developed as it approached our Sun were themselves messages written in gas and dust. As the comet warmed, different ices sublimated at different temperatures, creating a sequence of outgassing that told us about the comet's internal structure. Water ice sublimates at one temperature, carbon dioxide at another, carbon monoxide at yet another. By observing which gases appeared when, at what distances from the Sun, scientists could build a model of how 3i Atlas is constructed, how its various ices are layered or mixed together. The dust particles released from the comet as the ice sublimated are particularly interesting. These particles, lifted from the comet's surface by escaping gas, are pristine samples of the solid material that makes up 3i Atlas. Some of this dust might have fallen to Earth, tiny particles no bigger than specks of dust, carrying alien minerals to our planet's surface. It's entirely possible that somewhere on Earth, in Antarctic ice or deep ocean sediments, there are microscopic pieces of 3i Atlas waiting to be discovered, actual physical samples from another star system that we could hold in our hands, or at least under our microscopes. The rate at which 3I Atlas was losing mass as it passed through our inner solar system tells us about the strength and structure of its nucleus. Some comets are loosely bound rubble piles that fall apart easily when heated. Others are more solid, held together by stronger forces. The structural integrity of 3I Atlas tells us about the conditions under which it formed, whether it assembled gently in a quiet region of its home system, or was compacted by collisions and gravitational forces. This structural information is another piece of the puzzle, helping us understand not just what 3I Atlas is made of, but how it was put together. As we observed 3I Atlas, we were also looking for signs of heterogeneity, variations in composition across the comet's surface or interior. No comet is perfectly uniform. They often contain pockets of different ices, layers with varying dust-to-ice ratios, perhaps even voids and caverns in their interiors. These variations tell us about the comet's formation history, about how different materials were distributed in the protoplanetary disk where it formed, about subsequent processing and evolution. Each variation is a chapter in the comet's biography, a record of events and conditions from its past. The spin rate and orientation of 3I Atlas also carry information. How fast is it rotating? Is its spin axis stable or does it tumble chaotically? These dynamical properties tell us about the comet's collision history, about gravitational torques it has experienced, about outgassing events that might have changed its rotation. A comet spinning too fast might fly apart, so the fact that 3I Atlas remains intact tells us something about its internal strength. The orientation of its spin axis relative to its orbit tells us about the forces that have acted on it, both in its home system and during its interstellar journey. There's something profound about the fact that we can extract so much information from a brief encounter with a cosmic visitor. 3I Atlas spent only months in the inner solar system, where we could observe it closely, yet from those observations, we can reconstruct billions of years of history. It's as if the comet compressed its entire life story into a few months of testimony, speaking to us in the language of chemistry and physics, telling us about places and times we'll never directly experience. The organic chemistry of 3I Atlas is particularly fascinating when we consider the possibility of panspermia, the idea that life or its precursors can spread between star systems. While 3I Atlas shows no signs of carrying life itself, it does demonstrate that complex organic molecules can survive interstellar journeys lasting billions of years. If comets can carry organic molecules between star systems, they could potentially seed multiple worlds with the chemical building blocks of life. Perhaps life on Earth itself was sparked by organic molecules delivered by comets, though from our own solar system rather than interstellar ones. The preservation of these organic molecules through billions of years of interstellar travel tells us something important about the robustness of carbon chemistry. Despite exposure to cosmic rays, despite the extreme cold of interstellar space, despite the absence of any protective atmosphere or magnetic field, complex organic molecules in 3I Atlas survived intact. This resilience suggests that organic chemistry might be more common in the universe than we previously thought, that the building blocks of life might be scattered throughout the galaxy, waiting for the right conditions to assemble into something more complex. Some scientists have speculated about the possibility of finding even more complex chemistry in interstellar comets. Perhaps under the right conditions, the slow, patient chemistry that occurs even at temperatures near absolute zero could produce molecules of extraordinary complexity. The constant bombardment by cosmic rays provides energy for chemical reactions. The surfaces of dust grains can act as catalysts, bringing molecules together in ways that wouldn't happen in empty space. Over billions of years, who knows what chemical complexity might arise? There's also the intriguing possibility that 3I Atlas might carry information about life in its home system, even if it doesn't carry life itself. If its home system harbored a biosphere, that life would have affected the chemistry of the entire system. Life on Earth has dramatically altered our planet's atmosphere, filling it with oxygen, methane, and other gases that wouldn't exist in such abundance without biology. If 3i Atlas formed in a system with life, it might carry chemical signatures of that biosphere, unusual isotope ratios, organic molecules that are more commonly produced by biology than by non-biological chemistry. Perhaps even microscopic fossils if life in that system produced hard parts that could be preserved. The search for such biosignatures in 3i Atlas was unsuccessful, but that doesn't mean future interstellar visitors won't carry them. Each interstellar comet is a unique sample from a unique star system, and we've only observed a handful so far. As our detection capabilities improve, as we observe more interstellar visitors, we might eventually find one that carries unmistakable signs of life from another world. It would be the discovery of the millennium, proof that life exists elsewhere in the universe, delivered to our doorstep by a cosmic messenger. The minerals in 3i Atlas might also tell us about the geological processes in its home system. Different minerals form under different conditions. Some require liquid water, others form only in completely dry environments, some need high pressures, others form only at the surface. The mineral inventory of 3i Atlas could tell us whether its home system had planets with active geology, whether there were worlds with liquid water, whether there were processes we don't see in our own solar system. Each mineral grain is like a geological sample from an alien world, carrying information about conditions we can only imagine. The isotopic composition of elements in 3i Atlas tells us about the nuclear history of its material. Every element heavier than hydrogen and helium was forged in the nuclear furnace of a star or in the violent explosion of a supernova. Different stellar processes produce different isotope ratios. By measuring these ratios in 3i Atlas, we can work backward to understand what kinds of stars contributed material to its birth cloud. Was it enriched primarily by massive stars that exploded as supernovae, or by smaller stars like our Sun that shed their outer layers more gently? Or perhaps by exotic events like neutron star collisions that produce heavy elements through rapid neutron capture? This nuclear archaeology connects 3i Atlas to the broader history of element formation in the universe. The comet is made of atoms that have been recycled through multiple generations of stars, each generation adding new elements to the cosmic inventory. The carbon in its organic molecules might have been forged in a star that died billions of years before 3i Atlas formed. The oxygen in its water ice might have come from a different star entirely. The comet is a collection of atoms with different histories, brought together by chance and circumstance, now carrying their collective story through the galaxy. As you lie there in the darkness, perhaps feeling the weight of your own body made of atoms with similar cosmic histories, consider how 3i Atlas connects us to the broader universe. We too are made of elements forged in stars, assembled from the same cosmic inventory that created 3i Atlas. The hydrogen in the water in your body was formed in the Big Bang. The carbon in your DNA was created in the core of a star. The iron in your blood was forged in a supernova explosion. In a very real sense, we are cousins to 3i Atlas, sharing a common heritage in the stellar processes that created the elements. The messages carried by 3i Atlas aren't just scientific data points. They're reminders of our cosmic connections, evidence of the processes that link all matter in the universe. When we study the chemistry of an interstellar comet, we're studying our own deep history, learning about the processes that eventually led to our existence. Every molecule in 3i Atlas tells a story that's part of our own story, even though it comes from a completely different star system. The preservation of information in 3i Atlas through billions of years of interstellar travel demonstrates something profound about the nature of information in the universe. Information, it seems, is remarkably robust. It can be encoded in the arrangement of atoms in a molecule, in the isotopic composition of elements, in the crystal structure of minerals, and once encoded, it can survive almost indefinitely if protected from destruction. 3i Atlas is proof that information can travel between star systems, that messages can be passed across the galaxy even without any intention or design. This natural preservation and transmission of information might be a fundamental feature of the universe. Perhaps the cosmos is constantly writing and rewriting its own history, in the chemistry of comets and asteroids, in the light from distant stars, in the gravitational waves from colliding black holes. We're surrounded by messages from across space and time, most of which we don't yet know how to read, but occasionally something like 3i Atlas comes along, a message written clearly enough that we can begin to decipher it. The possibility that 3i Atlas might return carrying new information from its continued journey adds another layer to this cosmic communication system. If it does come back millions or billions of years from now, it won't be the same object that left. Its surface will have been further processed by cosmic rays. It might have accumulated new material from the interstellar medium. If it passes through other star systems, it might pick up traces of their chemistry. The returning 3i Atlas would be like a book with new chapters added, a message that has been annotated and expanded during its travels. As we continue to contemplate the messages carried by this interstellar visitor, remember that we're not passive recipients of these cosmic communications. By observing and studying 3i Atlas, we've become part of its story. Our sun's gravity has altered its trajectory. Our observations have extracted information from it. And if humanity or its descendants survive long enough, we might be here to witness its return, to read the new messages it has accumulated, to add another chapter to the ongoing dialogue between our solar system and this wandering messenger. The chemistry of 3i Atlas also raises philosophical questions about the nature of identity and change. Every atom in the comet has existed since the early universe, but their arrangement into molecules, their assembly into a comet, is relatively recent. Is 3i Atlas billions of years old, dating back to its atomic components? Or is it only as old as its formation as a distinct object? And as it loses material through outgassing, and possibly gains material from the interstellar medium, at what point does it stop being the same object? These questions don't have simple answers, but contemplating them helps us understand the fluid nature of identity in a universe where everything is constantly changing, yet nothing is ever truly destroyed. The messages in ice and stone that 3i Atlas carries are written in a language that transcends human words and concepts. It's the language of the universe itself, spoken in chemical formulas and isotope ratios, in crystal structures and molecular bonds. Learning to read this language is one of humanity's great scientific adventures, a quest to understand not just what the universe is made of, but how it communicates with itself across vast distances and times. And 3i Atlas, this frozen messenger from another star, has given us a precious opportunity to practice our reading skills, to decipher messages from a place we'll never see, written in a time before Earth existed. Throughout human history, we have been watchers of the sky, quiet observers of the cosmic dance playing out above our heads. Long before we understood what stars were, before we knew that planets were worlds like our own, before we comprehended the vast distances that separate us from even our nearest celestial neighbours, we watched. We watched and we wondered. We created stories and myths. We tried to find patterns and meaning in the lights that wheeled overhead each night. And now, with our modern instruments and understanding, we continue that ancient tradition, but with a depth and precision our ancestors could never have imagined. We have become the quiet watchers, the patient observers who scan the darkness for visitors like 3i Atlas, for messages from the cosmos that arrive without warning and depart just as suddenly. There's something deeply moving about the continuity of this practice, this unbroken chain of observation that connects us to the very dawn of human consciousness. When the astronomers who discovered 3i Atlas were scanning the sky through their telescopes and computer screens, they were participating in the same fundamental activity as the ancient Babylonians, who tracked the movements of planets, the Maya who predicted eclipses, the Aboriginal Australians who navigated by the stars. The tools have changed dramatically, but the essential human impulse remains the same: to look up, to observe, to try to understand our place in the cosmos. The discovery of 3i Atlas itself is a testament to how far we've come as watchers of the sky. It wasn't found by accident, but through systematic observation, through patient monitoring of the heavens night after night, year after year. The Asteroid Terrestrial Impact Last Alert System, ATLAS, from which the comet takes part of its name, consists of telescopes that automatically scan the sky, taking images and comparing them to previous observations, looking for anything that moves against the background stars. It's a kind of cosmic surveillance system, a network of unblinking eyes that never tire, never need sleep, never lose focus. Think about what this means. We've created mechanical extensions of our own vision that can watch the entire sky simultaneously, that can detect objects far too faint for human eyes to see, that can track motion too subtle for us to perceive directly. These instruments are like a new sense organ for humanity, allowing us to perceive aspects of the universe that would otherwise remain hidden. Through them, we've become aware of a cosmic traffic that has probably been flowing through our solar system since its formation, but which we've only recently developed the ability to see. The human story of discovering interstellar objects is remarkably recent. It was only in 2017 that we detected our first confirmed interstellar visitor, Oumuamua, that strange, elongated object that sparked so much speculation and wonder. Before that, we knew intellectually that such objects must exist, that stars must occasionally eject comets and asteroids just as our Sun does, and that some of these must pass through our solar system. But knowing something intellectually and actually observing it are very different experiences. When Oumuamua was discovered, it transformed interstellar visitors from theoretical possibilities to observed realities. The discovery of 2I Borisov in 2019 showed that Oumuamua wasn't a fluke, that interstellar visitors are a regular occurrence. And then came 3I Atlas, adding to our small but growing catalogue of confirmed interstellar objects. Each discovery has been a milestone, a reminder that we're getting better at watching, better at detecting these cosmic wanderers as they pass through our neighbourhood. But for every one we detect, how many slip by unseen? Current estimates suggest that there might be thousands of interstellar objects in our solar system at any given time, most too small or too distant to detect with our current technology. The patient vigilance required to detect objects like 3I Atlas is extraordinary. These objects don't announce their arrival with fanfare. They appear as tiny dots of light, barely distinguishable from the countless asteroids and comets that belong to our own solar system. It's only through careful observation of their motion, precise calculation of their orbits, that their interstellar nature becomes apparent. This requires not just powerful telescopes, but sophisticated software, careful data analysis, and the dedication of astronomers who spend their careers searching for these needles in the cosmic haystack. Consider the network of observers involved in studying 3I Atlas once it was discovered. Telescopes around the world turned toward this visitor, each contributing observations from their unique vantage points. Space-based telescopes, free from the distortion of Earth's atmosphere, provided the clearest images. Radio telescopes listened for any unusual emissions. Spectroscopes analyzed the light reflecting off the comet and passing through its coma, revealing its chemical composition. It was a global effort, a collaboration of quiet watchers all focused on the same small, distant object. This collaborative watching extends beyond professional astronomers. Amateur astronomers, those dedicated individuals who observe the sky for the love of it rather than as a career, also contributed observations of 3 Atlas. With modern equipment, talented amateurs can make scientifically valuable observations, tracking the comet's brightness changes, monitoring its coma development, even discovering new features that professional astronomers might have missed. There's something beautiful about this democratic aspect of astronomy, the fact that anyone with a telescope and dedication can contribute to our understanding of cosmic visitors. The role of computation in modern astronomical watching cannot be overstated. The amount of data generated by modern telescopes is staggering. Terabytes upon terabytes of images that no human could possibly examine individually. Instead, We've developed algorithms that can automatically detect moving objects, classify them, and flag anything unusual for human attention. These digital watches never blink, never get tired, never get distracted. They can compare an image taken tonight with one taken years ago, instantly detecting changes that would be invisible to human observers. Machine learning and artificial intelligence are becoming increasingly important in this cosmic vigil. These systems can be trained to recognize the subtle signatures of interstellar objects, to distinguish them from the far more numerous solar system objects. They can predict where an object will be in the future, allowing telescopes to be pointed in the right direction at the right time. They can even identify patterns in the data that human astronomers might not notice, potentially leading to new discoveries about the nature and behavior of interstellar visitors. But despite all this technology, there remains something irreducibly human about the practice of watching the sky. It's humans who decide what to look for, who interpret what the instruments detect, who feel the thrill of discovery when something new appears. The quiet watchers aren't just the telescopes and computers, but the people who operate them, who stay up through the night monitoring observations, who spend years of their lives searching for these cosmic needles in haystacks. Their patience and dedication are what make discoveries like 3I Atlas possible. The history of comet observations stretches back millennia, and many cultures have traditions of comet watching that blend scientific observation with spiritual significance. In ancient China, court astronomers kept detailed records of comets, noting their appearance, brightness, and path across the sky. These records, preserved for thousands of years, have proven scientifically valuable, allowing modern astronomers to calculate the orbits of periodic comets and understand how they've changed over time. The Chinese astronomers were quiet watchers par excellence, patiently recording celestial events for purposes both practical and philosophical. In medieval Europe, comets were often seen as omens, harbingers of change or disaster. While we now understand that comets are simply icy bodies following the laws of physics, there's something to be said for the medieval perspective that comets are messengers. They are indeed messengers, not of divine will but of cosmic processes, carrying information about the formation and evolution of planetary systems. The medieval watchers who fearfully or wondrously observed comets were responding to the same sense of significance that modern astronomers feel when they detect an interstellar visitor. The development of the telescope in the early 17th century revolutionized comet watching. Suddenly, observers could see details invisible to the naked eye: the structure of cometary tails, the changes in the coma, faint comets that would otherwise go unnoticed. Galileo observed comets through his telescope, though he incorrectly thought they were atmospheric phenomena. It was astronomers like Edmund Halley who realized that comets were celestial bodies orbiting the sun, and that some comets return periodically. Halley was a quiet watcher who used observations spanning decades to predict the return of the comet that now bears his name. The photographic revolution of the late 19th and early 20th centuries transformed comet watching again. No longer did astronomers have to rely on their eyes and hand-drawn sketches. Photographs could capture details too faint or fleeting for visual observation, and they provided a permanent record that could be studied and restudied. Many comets were discovered on photographic plates, appearing as fuzzy streaks against the star field. These photographic watchers could survey much larger areas of sky than visual observers, increasing the rate of comet discovery. The space age has given us new vantage points from which to watch for cosmic visitors. Telescopes in orbit around Earth, free from atmospheric interference, can detect fainter objects and observe in wavelengths blocked by our atmosphere. Space probes sent to study comets up close have revealed details we could never see from Earth. The actual shape and structure of cometary nucleon, the processes of outgassing and fragmentation, the complex interaction between comets and the solar wind. These robotic watchers extend our senses into space itself, allowing us to observe comets from perspectives our ancestors could only dream of. The Rosetta mission to Comet 67P Churyumov-Gerasimenko represents perhaps the ultimate in comet watching. A spacecraft that orbited a comet for over 2 years, observing every detail of its activity as it approached the Sun, reached perihelion, and receded back into the outer solar system. Rosetta watched the comet wake up from its frozen slumber, saw jets of gas and dust erupt from its surface, witnessed landslides and changes in surface features. It even deployed a lander, Philae, to observe the comet from its surface. This kind of intimate, long-term observation of a single comet has taught us more about cometary behavior than centuries of observation from Earth. But 3I Atlas and other interstellar visitors present unique challenges for watchers. Unlike periodic comets from our own solar system, which return predictably and can be observed over multiple orbits, interstellar visitors give us only one chance. They appear without warning, grace our skies briefly, and then disappear forever, or at least for billions of years. This makes every moment of observation precious. There's no opportunity to say, we'll get better data next time it comes around. There is no next time, at least not on human timescales. This urgency was evident in the global response to 3I Atlas's discovery. Observing time on major telescopes is planned months or years in advance, but when an interstellar visitor is detected, those plans are often set aside. Directors of observatories can declare target of opportunity observations, immediately redirecting telescopes to study these rare visitors. It's a recognition that some cosmic events are so rare, so scientifically valuable, that they justify disrupting carefully planned observing schedules. The quiet watchers who study objects like 3I Atlas aren't just collecting data for its own sake. They're trying to answer fundamental questions about our place in the universe. How common are planetary systems like ours? What processes eject comets into interstellar space? How does material travel between star systems? Are we alone, or is life common in the cosmos? Each observation of an interstellar visitor provides a piece of the puzzle, a clue to answering these profound questions. There's a meditative quality to astronomical observation that connects it to contemplative practices across cultures. The astronomer at the telescope, the data analyst studying images on a screen, the theorist working through calculations, all are engaged in a kind of cosmic contemplation. They're quietly watching the universe reveal itself, patient as monks in their dedication to understanding. The long hours, the careful attention to detail, the willingness to spend years or entire careers searching for rare events, these are the qualities of the quiet watcher. Modern technology has also democratized skywatching in unprecedented ways. Data from many astronomical surveys is made publicly available, allowing anyone with an internet connection to search for moving objects, variable stars, or other phenomena. Citizen science projects like Zooniverse engage thousands of volunteers in classifying galaxies, searching for exoplanets, and yes, looking for comets. These distributed networks of watchers multiply our ability to monitor the cosmos, turning sky watching from a professional activity into a global collaborative effort. The software and algorithms we use to detect objects like 3I Atlas are themselves a kind of watcher, tirelessly scanning data for patterns that might indicate something interesting. These digital watchers can process vast amounts of information, comparing millions of star positions, tracking thousands of moving objects, alerting human astronomers when something unusual appears. They're like an extension of our consciousness into the digital realm, watching with perfect attention every moment of every day. But there's still something special about human observation, about the moment when a person realizes they're seeing something extraordinary. The astronomer who first noticed that 3I Atlas's orbit was hyperbolic, that it wasn't bound to our sun, must have felt a thrill of discovery that no algorithm can experience. That moment of recognition, of understanding that you're looking at something from another star system entirely, connects modern astronomers to every human who has ever looked up at the sky in wonder. The quiet watchers also include the theorists who predict what we might see, who work out the physics of interstellar objects before they are observed. These scientists use computer simulations and mathematical models to understand how comets form, how they're ejected from star systems, how they travel through interstellar space, what they might look like when they pass through our solar system. When an object like 3I Atlas is discovered, these predictions can be tested against reality, advancing our understanding of cosmic processes. The instruments we use to watch the sky are becoming ever more sophisticated. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky every few nights, detecting moving objects far fainter than current surveys can see. The James Webb Space Telescope can observe in infrared wavelengths, potentially detecting the heat from interstellar objects far from the Sun. Future telescopes, some still in the planning stages, will have even greater capabilities. Each improvement in our watching ability reveals new aspects of the cosmos, new types of objects, new phenomena to understand. As our watching capabilities improve, we're likely to detect many more interstellar visitors. Some scientists estimate that once the Vera Rubin Observatory is operational, we might detect several interstellar objects per year. Each one will be an opportunity to learn about other star systems, to test our theories about planetary formation and evolution, to search for signs of unusual chemistry or even biology. The quiet watchers of the future will have a rich harvest of cosmic visitors to study. The cultural impact of discovering interstellar objects extends beyond science. Each detection reminds us that we're not isolated, that our solar system is part of a larger galactic community where material is constantly being exchanged between stars. It's a perspective shift similar to seeing Earth from space for the first time. Suddenly, our cosmic neighborhood doesn't seem so separate from the rest of the universe. The quiet watchers who detect these objects are expanding not just our scientific knowledge, but our cosmic perspective. There's also the tantalizing possibility that one day, the quiet watchers might detect something truly extraordinary, an interstellar object that shows unmistakable signs of artificial origin. While 3I Atlas appears entirely natural, the detection of interstellar visitors has renewed interest in the possibility of detecting alien artifacts passing through our solar system. Some scientists have proposed that advanced civilizations might send probes to other star systems, and that some of these probes might eventually pass through our neighborhood. The quiet watchers who scan the sky for natural interstellar objects are also, perhaps unknowingly, conducting a search for evidence of intelligence elsewhere in the universe. The patience required for this kind of watching is extraordinary. An astronomer might spend their entire career searching for a particular type of object or event and never find it, but they continue watching anyway, knowing that their observations contribute to the larger enterprise of understanding the cosmos. They're like gardeners tending a plot that might not bloom in their lifetime, but whose eventual flowering will benefit future generations. This long-term perspective, this willingness to work toward goals that might not be achieved for decades or centuries, is one of humanity's most admirable qualities. As you lie there in the darkness, perhaps you too are becoming a quiet watcher, your mind's eye turned toward the cosmos, contemplating the journey of 3I Atlas and objects like it. You don't need a telescope to participate in this ancient practice. Simply thinking about these cosmic visitors, wondering about their origins and destinations, imagining what other interstellar objects might be passing unseen through our solar system right now. This too is a form of watching. You're joining a tradition that stretches back to the dawn of humanity and forward to futures we can barely imagine. The story of the quiet watchers is also a story of technological evolution, of how we've extended our senses far beyond their biological limits. Our eyes can only see a tiny fraction of the electromagnetic spectrum, but our instruments can detect everything from radio waves to gamma rays. Our eyes can only see objects above a certain brightness, but our telescopes can collect light for hours, revealing objects billions of times fainter than we can see. Our eyes can only observe from one location, but we have telescopes scattered across Earth and throughout the solar system, providing multiple perspectives on cosmic events. This technological enhancement of our watching capabilities raises interesting philosophical questions. When we detect 3I Atlas using a telescope and computer system, Who or what is doing the watching? Is it the human astronomer who interprets the data? The computer algorithm that first identified the moving object? The telescope that collected the photons? Or is it all of these together, a hybrid human-machine watcher that represents a new phase in the evolution of consciousness? These questions don't have easy answers, but they point to the changing nature of what it means to observe the universe. The quiet watchers who study interstellar objects are also time travelers of a sort. When they observe 3i Atlas, they're seeing light that left the comet minutes ago. But they're studying an object that formed billions of years ago in another star system. They're piecing together a history that spans cosmic epochs, using observations made in mere moments to understand processes that unfold over eons. It's a kind of temporal archaeology, digging through layers of time preserved in the chemistry and dynamics of a comet. The international nature of modern astronomical watching is worth celebrating. When 3i Atlas was discovered, astronomers around the world immediately began collaborating, sharing data and insights across borders and time zones. Chinese telescopes observed it as it set in European skies. American astronomers analysed data collected by Australian observatories. It was a truly global effort, demonstrating that the quiet watchers form a worldwide community united by curiosity about the cosmos. In an era often marked by division and conflict, astronomy remains a sphere of international cooperation and shared wonder. As we've become better at watching for interstellar objects, we've also had to become better at distinguishing them from other phenomena. Not every unusual object is from another star system. Some comets from our own Oort cloud have orbits so elongated that they can initially appear hyperbolic. Some asteroids can receive gravitational kicks that temporarily put them on escape trajectories. The quiet watchers must carefully analyze each candidate, ruling out alternative explanations before confirming an interstellar origin. This careful, methodical approach is what makes their discoveries credible and valuable. The data collected by the quiet watchers studying 3i Atlas will be analysed for years, perhaps decades to come. Long after the comet has faded from view, scientists will be extracting new insights from the observations made during its brief visit. They'll be testing new theories against the data, developing better models of interstellar objects, preparing for future visitors. In this way, the watching continues even after the object itself is gone, a kind of contemplative observation that happens in computer models and theoretical calculations rather than at telescope eyepieces. The quiet watchers remind us that the universe rewards patience and attention. Cosmic events don't happen on human schedules. Interstellar visitors don't arrive when it's convenient for us to observe them. The universe unfolds at its own pace, indifferent to our desires or expectations. But for those willing to watch patiently, to maintain their vigil through long nights and years of non-detection, the cosmos occasionally offers spectacular rewards. A visitor from another star, a messenger from across the galaxy, a glimpse of worlds we'll never see directly. As we prepare to explore the deeper patterns and cycles that govern cosmic motion, remember the human dimension of these discoveries. Behind every detection of an interstellar object, behind every measurement and calculation, there are quiet watchers, people who have dedicated their lives to observing the universe, to being the eyes through which humanity sees the cosmos. Their patience, dedication, and wonder are what transform points of light in the sky into stories of cosmic journeys, into connections with distant stars, into reminders of our place in a vast and ancient universe. Everything in the universe moves in cycles, from the smallest subatomic particles oscillating at frequencies beyond imagination to the grandest structures of the cosmos, wheeling through space in patterns that span billions of years. As you rest there in the peaceful darkness, your own body participating in countless cycles, the rhythm of your breath, the beating of your heart, the electrical pulses travelling through your neurons. Consider how 3i Atlas and its possible return represents just one example of the infinite loops and spirals that define existence itself. The universe, it seems, has a fundamental preference for circular motion, for patterns that repeat with variations, for endings that become beginnings in an eternal dance of matter and energy through space and time. At the most fundamental level, everything is vibration, oscillation, cycles within cycles. The electrons in atoms don't orbit their nuclei in simple circles as we once imagined, but exist in probability clouds that pulse and shimmer with quantum uncertainty. Yet even in this quantum realm, there are patterns, frequencies, resonances that repeat with mathematical precision. The photons of light that carried the image of 3i Atlas to our telescopes are themselves oscillations, electromagnetic waves cycling through their frequencies billions or trillions of times per second. The very fabric of space-time ripples with gravitational waves, cosmic vibrations spreading outward from colliding black holes and neutron stars, carrying their cyclic patterns across the universe. When we observe 3i Atlas following its path through space, we're watching one cycle nested within countless others. The comet rotates on its axis, perhaps completing a rotation every few hours or days. We don't know its exact period, but it surely spins, as almost everything in the universe does. This rotation is itself a memory of the comet's formation, preserving angular momentum from the swirling disk of material where it was born billions of years ago. As it spins, different faces of the comet are exposed to sunlight and shadow, to the solar wind and cosmic rays, creating daily cycles of heating and cooling that have been repeating throughout its journey. But this spinning comet is also orbiting through the galaxy, participating in a much grander cycle. Even though 3i Atlas isn't bound to our sun or any other star, it's still bound to the galaxy itself, following an orbit around the galactic center that might take hundreds of millions of years to complete. This galactic orbit isn't a simple ellipse like planetary orbits around stars. It's a complex rosette pattern, influenced by the combined gravity of billions of stars, by the spiral density waves that create the galaxy's arms, by encounters with giant molecular clouds and star clusters. The comet's path through the galaxy is like an elaborate dance, never quite repeating exactly but following patterns that echo and rhyme across cosmic time. The galaxy itself is rotating, carrying 3i Atlas and everything else within it in a vast spiral dance. But even this isn't the largest cycle involved. Our galaxy is part of the local group, a collection of galaxies bound together by gravity, all orbiting their common center of mass. The local group is part of the Virgo supercluster, which is itself moving towards something called the Great Attractor, a gravitational anomaly hundreds of millions of light-years away. Cycles within cycles within cycles, each one operating on a different time scale, all of them interconnected in a cosmic symphony of motion. Consider how the concept of return, which we've been contemplating with 3i Atlas, appears at every scale in the universe. Halley's Comet returns every 76 years, marking human lifetimes with its appearances. The planets return to the same positions relative to each other in cycles that ancient astronomers called grand conjunctions. The Sun itself oscillates slightly as it orbits the galaxy, bobbing up and down through the galactic disk in a cycle that takes about 60 million years. Some scientists have suggested that these oscillations might correlate with mass extinction events on Earth, as our solar system periodically passes through regions of higher cosmic ray density, or encounters more interstellar material. There's something deeply satisfying about these cosmic cycles, something that resonates with patterns we observe in our own lives. We experience daily cycles of waking and sleeping, monthly cycles of the moon, yearly cycles of the seasons. Our bodies have circadian rhythms aligned with Earth's rotation, circannual rhythms aligned with its orbit around the sun. We're creatures of cycles, and perhaps that's why the idea of 3i Atlas returning feels intuitively right, even if intellectually we know the odds are astronomical. The universe has taught us to expect returns, to look for patterns that repeat, to find comfort in the reliability of cycles. The mathematical description of these cycles reveals beautiful patterns and unexpected connections. The orbits of planets and comets can be described by Kepler's laws, elegant mathematical relationships that connect orbital periods to distances, that explain why objects move faster when closer to the gravitational center and slower when farther away. These same laws that govern our solar system's planets also govern 3i Atlas's motion through the galaxy, just on vastly different scales. The mathematics is scale invariant, working equally well for moons orbiting planets, planets orbiting stars, stars orbiting galactic centers, and galaxies orbiting within clusters. Resonances between different cycles create some of the most interesting patterns in the cosmos. When two orbital periods are related by simple ratios, 1, 2, 2, 3, 3, 4, the objects can become locked in a gravitational dance that stabilizes their orbits. Jupiter's moons, Io, Europa, and Ganymede, are locked in a 1.2.4 resonance, their orbital periods precisely related to each other. Similar resonances exist throughout the solar system, throughout the galaxy, creating islands of predictability in what might otherwise be chaos. If 3i Atlas were to become trapped in such a resonance with our solar system's motion through the galaxy, it could create a pattern that brings it back to our neighborhood repeatedly over cosmic time. The concept of the eternal return appears in many philosophical and religious traditions. The idea that time itself might be cyclical, that events repeat endlessly in infinite variations. The ancient Greeks had their concept of the great year, after which the cosmos would return to its initial configuration. Hindu cosmology speaks of kalpas, vast cycles of creation and destruction, each lasting billions of years. Modern cosmology has its own version in the idea of cyclic universes, cosmological models where the Big Bang is followed by expansion, then contraction, then another Big Bang, in an endless cycle of cosmic rebirth. Whether or not time itself is cyclical, we observe cyclical patterns everywhere we look. Stars are born from clouds of gas and dust, live their lives fusing hydrogen into heavier elements, and die in various ways depending on their mass. But their death seeds space with the materials for new stars, new planets, new comets like 3i Atlas. It's a cycle of stellar life and death that has been repeating for billions of years and will continue for trillions more. Every atom in 3i Atlas except hydrogen has been through this cycle at least once, forged in one star, expelled into space, incorporated into a new star system, and perhaps destined to repeat the cycle again in the far future. Water, which makes up much of 3i Atlas's mass, follows its own cycles on cosmic and planetary scales. In our solar system, water cycles between ice in comets, liquid in planetary oceans, and vapor in atmospheres. Comets deliver water to planets, where it participates in weather cycles, geological cycles, perhaps biological cycles if life is present. Eventually, some of that water escapes back to space, where it might be incorporated into new comets. The water molecules in 3i Atlas have likely been through many such cycles in different star systems, and if the comet returns to our solar system or visits others, those molecules will continue their cosmic cycling. The organic molecules in 3i Atlas participate in what might be the most profound cycle of all, the cosmic organic cycle. Carbon atoms forged in stars become part of simple molecules in interstellar space. These molecules are incorporated into comets and asteroids, which deliver them to planetary surfaces. Under the right conditions, these simple molecules might become part of more complex chemistry, perhaps even contributing to the origin of life. Living things process these molecules, creating even more complexity, until death returns them to simpler forms. Some of these molecules escape back to space, where the cycle begins again. It's a vast, slow cycle that connects nuclear physics to biology, stars to living cells, the cosmos to consciousness. The possibility of 3i Atlas returning represents a particularly interesting type of cycle. Not a regular, predictable return like a periodic comet, but a chaotic return, unpredictable in its timing but perhaps inevitable given enough time. Chaos theory tells us that in complex dynamical systems, trajectories that diverge can sometimes converge again, that paths through phase space can loop back on themselves in unexpected ways. The three-body problem, which governs how 3I Atlas interacts gravitationally with stars it passes, is famous for producing such chaotic but sometimes recurring solutions. There's a beautiful theorem in dynamics called the Poincaré recurrence theorem, which states that certain systems will, given enough time, return arbitrarily close to their initial conditions. While the theorem doesn't directly apply to 3I Atlas's journey through the galaxy, the system is too open, too complex. It points to a general principle that seems to hold throughout the universe, that return is not just possible, but, given enough time, probable. The universe has a kind of memory encoded in the conservation laws of physics, and this memory creates the possibility of cycles and returns. The spiral structure of our galaxy itself represents a kind of cycle, though not in the way you might initially think. The spiral arms aren't fixed structures, but density waves that rotate through the galaxy at a different rate than the stars themselves. Stars and gas clouds pass through these density waves, experiencing compression that triggers star formation, then emerge on the other side to continue their orbits. It's like a cosmic traffic jam that maintains its pattern even as individual cars pass through it. 3I Atlas, in its journey through the galaxy, will pass through these spiral arms multiple times, each passage potentially altering its trajectory and perhaps increasing or decreasing the likelihood of its return to our neighborhood. The cycles we observe in the universe aren't perfect repetitions. Each orbit is slightly different from the last. Each cycle carries the memory of what came before. This is perhaps most beautifully illustrated by the precession of orbits. Earth's orbit around the Sun precesses, meaning the point of closest approach slowly rotates around the Sun over thousands of years. The same is true for every orbiting body, including 3I Atlas in its complex path through the galaxy. These precessions mean that no orbit ever exactly repeats, but instead traces out beautiful flower-like patterns in space over time, cycles that are similar but never identical. This concept of cycles with variations is fundamental to how complexity emerges in the universe. If everything simply repeated exactly, there would be no evolution, no development, no possibility for new structures and phenomena to emerge. But cycles with small variations, orbits that precess, resonances that slowly evolve, these create the conditions for complexity to build over time. The solar system we see today, with its elaborate architecture of planets, moons, asteroids, and comets, emerge from countless cycles of orbital evolution, each cycle building on the last. The human discovery and observation of cosmic cycles represents its own kind of cycle. Ancient astronomers noticed the regular motions of celestial bodies and used them to create calendars, to predict eclipses, to navigate. Each generation built on the observations of the previous one, gradually refining our understanding of cosmic motions. The discovery of 3I Atlas and other interstellar objects represents the latest chapter in this ongoing cycle of observation and understanding. Future generations will build on our observations, perhaps tracking interstellar visitors we can barely detect, perhaps even witnessing the return of 3I Atlas itself. There's a poetic symmetry in the idea that 3I Atlas, having completed countless cycles around its home star before being ejected, then travelling through the galaxy in vast loops around the galactic centre, might return to complete another kind of cycle by revisiting our solar system. It would be like a musical theme that appears early in a symphony, disappears for a long development section, then returns transformed but recognizable in the final movement. The universe seems to love these kinds of patterns, these echoes and returns that create structure and meaning from what might otherwise be random motion. The cycles within our own solar system create a kind of clockwork that marks the passage of time on various scales. The moon's phases give us months, Earth's orbit gives us years, the orbits of the outer planets mark decades and centuries. The precession of Earth's axis creates a 26,000-year cycle that slowly changes which stars appear at the poles. The entire solar system oscillates through the galaxy's disk on a roughly 60 million-year cycle. These nested cycles create a complex temporal structure, a natural calendar written in celestial motions. If 3i Atlas returns, it will arrive to find these cycles in different phases, the cosmic clock showing a different time, but the fundamental pattern still recognizable. Consider how the concept of cycles challenges our linear perception of time. We tend to think of time as an arrow, always pointing from past to future, never reversing or repeating. But the cycles we observe in the universe suggest a different model, one where time has a structure, where past and future can be connected through periodic returns. When we see 3i Atlas, we're seeing something from the deep past, an object formed billions of years ago, but we're also potentially seeing something from the far future, if it indeed returns. The comet exists in a kind of temporal loop, its past and possible future connected through the cycles of its motion. The search for patterns and cycles in astronomical data has revealed unexpected connections across vast scales of space and time. Scientists have found correlations between solar activity and climate on Earth, between the orbital cycles of planets and the distribution of asteroids, between the galaxy's rotation and the formation of stars. These connections suggest that the universe is more integrated, more interconnected than we might have thought. A change in one cycle can propagate through the system, affecting other cycles in subtle but measurable ways. 3i Atlas, in its journey through these interconnected cycles, is both affected by them and affects them in return, adding its small gravitational influence to the complex dance of celestial mechanics. The biological cycles on Earth provide an interesting parallel to the cosmic cycles we've been discussing. Life has its own periods and rhythms, reproductive cycles, predator-prey oscillations, evolutionary cycles of adaptation and extinction. Some scientists have suggested that these biological cycles might be influenced by cosmic cycles, that impacts from comets and asteroids might drive evolutionary change, that variations in cosmic ray flux might affect mutation rates. If this is true, then visitors like 3i Atlas aren't just participating in physical cycles, but potentially in biological ones as well, delivering materials or energy that could influence the development of life. The discovery of exoplanets has revealed that planetary systems themselves come in cycles of configurations. Hot Jupiters spiral inward toward their stars, planets migrate through their systems, exchanging angular momentum. Entire planetary systems can become unstable and reorganize themselves into new configurations. The system that gave birth to 3i Atlas has undoubtedly gone through such cycles of planetary reorganization, and these cycles might have been what ultimately ejected the comet into interstellar space. Our own solar system has likely experienced similar reorganizations, though on a smaller scale, and may experience them again in the future. As we contemplate these cycles within cycles, it's worth remembering that we ourselves are part of these patterns. The carbon in our bodies has cycled through stars and interstellar space. The water in our cells has been part of comets and oceans. We're temporary arrangements of atoms that have been cycling through different forms for billions of years and will continue cycling long after we're gone. In contemplating the possible return of 3i Atlas, we're really contemplating our own participation in these cosmic cycles, our brief moment of consciousness in an eternal dance of matter and energy. The mathematical beauty of orbital cycles extends to something called action angle variables, a way of describing motion that makes the cyclic nature of orbits explicit. In this formulation, the motion of any orbiting body can be described as movement around a torus, a donut-shaped surface in mathematical space. The position on this torus determines the object's location and velocity in real space. Objects with regular orbits trace out simple paths on this torus, while chaotic orbits create complex space-filling patterns. 3i Atlas's path through the galaxy if we could visualize it in this action angle space, would be an incredibly complex pattern, perhaps eventually filling the entire available space, but always confined to the torus defined by its energy and angular momentum. The concept of ergodicity in dynamical systems suggests that, given enough time, a system will explore all possible states consistent with its conservation laws. If 3i Atlas's motion through the galaxy is ergodic, then over infinite time it will pass arbitrarily close to every point it's possible for it to reach. This includes passing arbitrarily close to our solar system again, perhaps many times. The universe has plenty of time, trillions of years before the last stars burn out, for such ergodic exploration to occur. In this view, the return of 3 Atlas isn't just possible, but, given enough time, almost certain. The cycles we observe in the universe also appear in the theoretical structures we use to understand it. Physical theories often have cyclic symmetries. Gauge theories that describe fundamental forces are based on symmetry groups that have cyclic properties. String theory, one attempt at a theory of everything, describes particles as vibrating strings, with different modes of vibration corresponding to different particles. Even our mathematical tools, from trigonometric functions to Fourier analysis, are fundamentally about decomposing complex phenomena into simple cycles. It's as if the universe and our understanding of it are built from cycles all the way down. As you continue to relax into the rhythm of these cosmic cycles, feeling perhaps your own breathing naturally synchronizing with the peaceful cadence of these thoughts, consider how the eternal return of celestial objects like 3i Atlas connects to deeper questions about the nature of existence. If the universe is infinite in time, if it continues expanding forever or cycles through endless big bangs and big crunches, then every possible configuration of matter and energy will eventually occur. Somewhere, somewhen, there will be another comet exactly like 3i Atlas, another solar system exactly like ours, another moment exactly like this one. The cycles guarantee it, even if the repetition takes googles of years. This idea of eternal recurrence raises profound philosophical questions. If everything eventually repeats, what does that mean for concepts like progress, meaning, and purpose? Perhaps the answer lies not in the repetition itself, but in the variations, the small differences that make each cycle unique even as it echoes previous ones. 3i Atlas, if it returns, won't be exactly the same. It will have been changed by its journey, just as our solar system will have changed. The return would be a rhyme, not a repetition, and in that difference lies the possibility for novelty, for evolution, for meaning. The study of cycles in complex systems has revealed that many systems naturally evolve towards cyclic attractors, stable patterns that the system settles into regardless of initial conditions. These limit cycles, as they're called, represent a kind of destiny for dynamical systems, a final pattern toward which they're drawn. Perhaps the galaxy as a whole has such attractors, stable patterns of stellar motion that, once established, persist for billions of years. If 3i Atlas has found its way into one of these patterns, its return might not be a chance event but an inevitable consequence of the galaxy's dynamical structure. The cycles within cycles that govern 3i Atlas's motion create what mathematicians call a quasi-periodic orbit, a path that never exactly repeats, but comes arbitrarily close to repetition over time. These orbits create beautiful patterns when visualized, intricate designs that seem almost artistic in their complexity. The universe, it seems, is not just a machine grinding through predictable cycles, but an artist creating ever-new variations on eternal themes. Each pass of 3i Atlas through the galaxy adds another line to this cosmic artwork, another thread in the tapestry of celestial motion. In the quiet moments of contemplation, when we allow our minds to drift among the stars and consider the vastness of space and time, we begin to understand that the universe speaks to us not through words, but through wonders, through mysteries that invite us to dream rather than demanding we solve them. 3i Atlas. This visitor from beyond our solar system carries with it dreams we can barely imagine. Dreams of other worlds, other suns, other possibilities for how matter and energy can organize themselves into patterns of beauty and complexity. As you rest there in the darkness, perhaps feeling sleep beginning to gently pull at the edges of your consciousness like gravity drawing a comet into a long, peaceful orbit, let yourself dream along with the cosmos, wondering what dreams may come when we truly understand our place in this infinite dance. What dreams might be frozen in the ice of 3i Atlas? If we could decode every molecule, every isotope, every grain of dust embedded in its ancient matrix, what stories would they tell? Perhaps they would speak of a young star system filled with promise, where planets were just beginning to form and the chemistry of life was taking its first tentative steps. Perhaps in that distant system, billions of years ago, there were warm pools where organic molecules were learning to replicate, or deep ocean vents where chemical gradients were driving the first metabolic processes. The comet might carry within it the dreams of life that never quite came to be, or perhaps the remnants of life that flourished and faded before Earth even existed. There's something profoundly moving about the idea that 3i Atlas might carry the unfulfilled potential of another world. Every planetary system begins with similar ingredients: hydrogen and helium from the Big Bang, heavier elements from previous generations of stars, organic molecules formed in interstellar space. But the specific conditions in each system determine whether those ingredients become living worlds or remain sterile collections of rock and ice. 3i Atlas formed in conditions just different enough from our own solar system to produce its unique chemistry, its particular blend of ices and organics. In another timeline, under slightly different circumstances, the material in this comet might have become part of a living world, contributing to oceans and atmospheres and perhaps even biology. When we dream about the possible return of 3i Atlas, we're really dreaming about second chances, about opportunities that come around again after seeming lost forever. The universe, through its patient cycles and vast timescales, offers these second chances on a cosmic scale. A comet ejected from its home system gets to visit other stars. Elements forged in one star get to become part of new stellar systems. And perhaps, just perhaps, objects that have wandered the galaxy for billions of years get to return to places they've visited before, changed by their journeys but still recognizable, like old friends returning after a long absence. The dreams we project onto cosmic objects like 3i Atlas tell us as much about ourselves as about the universe. We see in this interstellar visitor a reflection of our own wanderings, our own desire to explore and understand, our own hope that journeys have meaning even when their destinations are uncertain. The comet becomes a metaphor for the human condition, cast out from our origins, travelling through a vast and often dark universe, searching for meaning and connection, hoping that our journey has purpose even if we can't see the final destination. Consider the dreams of the astronomers who first detected 3i Atlas, who realized they were looking at something from another star system entirely. For them, this discovery was the culmination of careers spent searching the sky, of nights spent at telescopes or analyzing data, of dreams about what might be out there waiting to be discovered. Every astronomer dreams of making a discovery that advances human knowledge, and finding an interstellar visitor certainly qualifies. But beyond personal achievement, there's the larger dream of understanding our place in the cosmos, of knowing whether we're alone or part of a vast community of worlds. The possibility that 3i Atlas might return raises questions about what dreams we're planting for future generations. If the comet does come back in millions or billions of years, who or what will be here to observe it? Will it be our distant descendants, evolved beyond current recognition, but still carrying the spark of curiosity that makes us human? Will it be artificial intelligences we've created, patient observers who can wait millions of years for cosmic events? Or will Earth be observed by entirely different beings, visitors from other stars who happen to be present when 3i Atlas makes its return journey? We can dream about what message we might want to send to those future observers. If we could somehow mark 3i Atlas, leave some trace that would survive its journey through the galaxy, what would we want to say? We were here. We saw you. We wondered about you. Perhaps the very fact that we observed and studied the comet, that we incorporated it into our scientific understanding and our cosmic mythology, means that in some sense we've already left our mark. The comet has been changed by its encounter with our solar system, not just gravitationally but informationally. It has become part of human consciousness, and perhaps that connection transcends physical marking. The dreams inspired by interstellar visitors extend to the possibility of interstellar travel itself. Every time we detect an object that has traveled between stars, we're reminded that such journeys are possible, even if they take billions of years. Perhaps one day humans or our descendants will undertake such journeys, either in generation ships that take millions of years to reach their destinations, or through technologies we can't yet imagine. When we look at 3i Atlas, we're looking at proof that matter can survive interstellar journeys, that the vast spaces between stars are crossable, given enough time and patience. There's also the dream of communication across cosmic distances. While 3i Atlas appears to be a natural object with no signs of artificial modification, its very existence demonstrates that physical objects can carry information between star systems. Some scientists have proposed that advanced civilizations might deliberately launch objects into interstellar space as a way of communicating with other civilizations, a kind of message in a bottle cast into the cosmic ocean. These hypothetical objects, sometimes called Bracewell probes after the scientist who proposed them, would be like artificial comets, carrying not just chemical information but deliberate messages from one civilization to another. The dream of finding such an artificial object among the natural interstellar visitors is one that captures many imaginations. What if one day our patient sky watchers detect an object whose trajectory or composition clearly indicates artificial origin? What if we find something that couldn't have formed naturally, that shows unmistakable signs of engineering or intention? It would be the discovery that changes everything, proof that we're not alone in the universe, that other minds have looked up at the stars and wondered just as we do. But even without such dramatic discoveries, objects like 3i Atlas fulfill a different kind of dream, the dream of connection across impossible distances. When we study this comet, we're learning about conditions in another star system, possibly one on the other side of the galaxy. We're connected to that distant place and time through this messenger, this ambassador of ice and rock. It's a reminder that despite the vast distances that separate stars, despite the impossibility of faster-than-light travel, the universe has found ways to connect its disparate parts. Matter and information flow between star systems, slowly but inevitably, creating a kind of cosmic communication network. The dreams we have about the future of humanity often involve spreading among the stars, becoming a multi-stellar species. But perhaps there's another kind of spreading that's already happening, a diaspora of molecules and minerals, of chemical information and preserved history. Every interstellar object is part of this slow diffusion of matter through the galaxy. The atoms in 3i Atlas will eventually, through whatever process, become part of other objects, other star systems, perhaps other comets that will themselves become interstellar travelers. In this way, the material of the universe is constantly being shuffled and reshuffled, creating new combinations and possibilities. What dreams might come if we could somehow ride along with 3i Atlas on its journey through the galaxy? Imagine experiencing those billions of years of travel, watching stars being born and dying, seeing the spiral arms of the galaxy rotate past, witnessing the slow evolution of stellar populations. You would see regions of space no Earth-based observer will ever see, pass through environments we can only theorize about. You would accumulate experiences and observations that span cosmic epochs, becoming a repository of galactic history. Of course, such a journey would be incompatible with human consciousness as we know it. But perhaps there are other forms of awareness, other ways of experiencing time that would make such journeys not just bearable but meaningful. Perhaps the universe itself has a kind of consciousness, a slow, patient awareness that unfolds over billions of years. Perhaps objects like Three-Eye Atlas are the universe's way of experiencing itself, of carrying information, and perhaps even some form of awareness from one region to another. These are dreams that border on philosophy or even mysticism, but they emerge naturally from contemplating the journey of an interstellar comet. When we think about 3E Atlas travelling alone through the darkness for billions of years, we can't help but project onto it our own fears and hopes about isolation and connection, about purpose and meaning. The comet becomes a screen onto which we project our deepest questions about existence. The dream of return, which we've been exploring throughout our contemplation, taps into one of humanity's most powerful mythological themes. The hero's journey, found in stories across all cultures, involves leaving home, having adventures, and eventually returning transformed. Three-Eye Atlas has certainly left home and is having adventures as it travels through the galaxy. If it returns to our solar system, it will complete this archetypal journey, coming back to a place it has been before, but seeing it with new eyes, or rather being seen by new eyes, as whoever observes its return will not be the same as those who saw it leave. There's also the dream of persistence, of survival against impossible odds. 3 Atlas has survived billions of years in the harsh environment of interstellar space, exposed to cosmic rays, passing through who knows what dangers. Its survival gives us hope that delicate things, like organic molecules, like information, perhaps like life itself, can persist through almost any challenge given the right protection. The comet's icy shell has preserved its contents like a cosmic seed vault, maintaining the potential for chemistry and perhaps even biology across incomprehensible spans of time. What dreams may come when we fully understand the implications of interstellar visitors? Perhaps we'll discover that they're far more common than we thought, that our solar system is constantly being visited by objects from other stars. Perhaps we'll develop the technology to intercept and study them up close, to land on them and sample their materials directly. Perhaps we'll even find ways to hitch rides on them, using them as slow but free transportation to other star systems. These dreams might seem fantastic now, but remember that powered flight, space travel, and many other achievements of our species once seemed equally impossible. The dreams inspired by 3-Eye Atlas also include nightmares, fears about what interstellar visitors might bring. Could they carry dangerous materials, exotic matter that could threaten Earth? Could they be harbingers of cosmic catastrophes we don't yet understand? These fears, while generally unfounded based on our current understanding, are part of the complete emotional response to these cosmic visitors. They remind us that the universe, for all its beauty and wonder, can also be dangerous and unpredictable. But perhaps the most profound dream inspired by 3-Eye Atlas is the dream of cosmic citizenship, the recognition that we're part of something vastly larger than our single planet or even our single solar system. When we observe interstellar visitors, we're participating in a galactic community, even if it's a community where the members are separated by vast distances and communicate only through these slow, patient messengers. We're not isolated on Earth, but connected to every star we see, and many we don't, linked by the constant exchange of matter and energy, information and possibility. As sleep continues to approach, carrying you toward your own nightly journey through dreams, consider how the story of 3-Eye Atlas mirrors the journey of consciousness itself. Thoughts and ideas travel from mind to mind, sometimes lying dormant for generations before re-emerging in new forms. Knowledge is discovered, lost, and rediscovered. Civilizations rise and fall, but their ideas can survive in texts and traditions, waiting to inspire future generations. Perhaps consciousness itself follows cycles and patterns similar to those of celestial objects, with ideas and insights following long orbits through the space of possible thoughts, sometimes returning to inspire new understanding. The dream of 3i Atlas's return is really a dream about the continuity of existence, about connections that transcend the apparent isolation of objects in space and moments in time. It's a dream that says nothing is ever truly lost, that everything is connected in ways we're only beginning to understand, that the universe has a memory and a purpose even if we can't fully grasp them. When we wonder about this cosmic visitor and its possible return, we're participating in the universe's own dream of itself, adding our small voice to the vast conversation between stars and civilizations, between past and future, between what is and what might be. What dreams may come in the far future when 3i Atlas perhaps returns. By then, humanity might have spread throughout the galaxy, or we might have transcended physical existence entirely, becoming beings of pure information or energy, or we might be gone, our place taken by others who will wonder about this returning comet just as we wonder about it now. But whatever form consciousness takes in that distant future, it will likely still dream, still wonder, still seek to understand its place in the cosmos. And 3i Atlas, patient traveller that it is, will be there to inspire those dreams, to provoke those questions, to remind whatever minds exist that the universe is vast and ancient and full of wonders. The universe reveals itself to us not as a machine grinding through predetermined motions, but as a vast breathing entity, where every part is connected to every other part through invisible threads of gravity, light, and time. As we listen to the cosmic symphony, and we are listening, with our telescopes and our theories, our patient observations and our wild speculations, we begin to hear recurring themes, melodies that appear and disappear and reappear transformed. 3i Atlas is one note in this infinite composition, a single voice in a chorus of billions, yet its solo passage through our solar system has taught us to listen more carefully to the music of the spheres, to appreciate the harmonies and dissonances that create the richness of cosmic existence. There is an ancient idea, dating back to Pythagoras and perhaps even earlier, that the celestial bodies create music as they move through space. The medieval philosophers called it the musica universalis, the harmony of the spheres. They imagined that each planet, each star, each celestial object emitted a tone determined by its orbital properties, and that together these tones created a cosmic harmony, too perfect for human ears to perceive. We now know that celestial bodies don't literally sing as they move through the vacuum of space, but in a deeper sense the idea of cosmic music has proven remarkably prescient. Everything in the universe vibrates at characteristic frequencies. Atoms vibrate as their electrons jump between energy levels. Molecules vibrate as their bonds stretch and compress. Asteroids and comets tumble with regular periods. Planets orbit with clockwork precision. Stars pulsate, some with periods of seconds, others with periods of years. Galaxies rotate on timescales of hundreds of millions of years. Even space-time itself vibrates with gravitational waves spreading outward from cosmic collisions. If we could translate all these vibrations into sound, the universe would indeed be filled with music, a symphony of frequencies spanning from the ultrasonic to the infrasonic, and far beyond. 3i Atlas contributes its own notes to this cosmic symphony. Its rotation creates one frequency, its orbital motion through the galaxy another. The molecules in its ice vibrate at their characteristic frequencies, creating spectral signatures we can detect with our instruments. As the comet warmed during its passage through our inner solar system, the sublimating gases created their own harmonics, jets of vapor spinning the comet faster or slower, changing its tune. Even the dust particles released from its surface had their own frequencies, determined by their size and composition and the forces acting upon them. But the symphony of the spheres isn't just about individual notes, it's about the relationships between them, the harmonies and resonances that emerge when different frequencies interact. When two orbiting bodies have periods related by simple ratios, they create gravitational resonances that can stabilize or destabilize their orbits. These orbital resonances are like musical harmonies, creating structure and pattern from what might otherwise be chaos. The asteroid belt has gaps where orbital resonances with Jupiter have cleared out material. Neptune and Pluto are locked in a 3-2 resonance that prevents them from ever colliding despite their crossing orbits. These resonances are the universe composing music with gravity as its instrument. The possibility of 3I Atlas returning to our solar system would represent a kind of musical return, like a theme that appears at the beginning of a symphony and comes back in the finale. But it wouldn't be an exact repetition. The theme would be transformed by its journey through the development section, enriched with new harmonies, played in a different key perhaps, but still recognizable. The comet would return changed by its travels, and it would return to a solar system that had also changed, creating new harmonies from the interaction of old and new. Consider the mathematical beauty of orbital mechanics as a kind of musical score. Kepler's laws, which describe planetary motion, can be expressed as mathematical relationships that are remarkably similar to the mathematics of musical harmony. The inverse square law of gravitation creates patterns that mirror the harmonic series in music. The Fourier analysis we use to decompose complex orbital motions into simple periodic components is the same mathematics we use to understand musical timbre and harmony. It's as if the universe and music are written in the same mathematical language. The detection of 3I Atlas required us to listen carefully to the cosmic symphony, to pick out its faint note from the background noise of asteroids and distant stars. Our telescopes are like sensitive microphones. Our computers like audio processors that can isolate and amplify specific frequencies. When astronomers discovered that 3I Atlas was on a hyperbolic orbit, they were essentially recognizing that it was playing in a different key than the objects bound to our solar system, that its frequency didn't fit the local harmony. The Doppler shift of light from moving objects is directly analogous to the Doppler shift of sound. As 3I Atlas approached us, its light was blue shifted to higher frequencies, and as it receded, it was red shifted to lower frequencies. We literally heard the comet's motion in the changing pitch of its light. This cosmic Doppler effect allows us to measure the velocities of stars and galaxies, to hear the expansion of the universe itself in the red-shifted light from distant objects. The universe is constantly telling us about its motion through these frequency shifts, singing its story in wavelengths of light. The concept of harmonics extends to the structure of atoms themselves. Electrons in atoms can only occupy specific energy levels, like notes on a musical scale. When electrons jump between these levels, they emit or absorb photons at specific frequencies, creating the spectral lines we use to identify elements in distant objects. The spectrum of 3I Atlas is like its musical signature, telling us what elements are present and in what states. Each molecule has its own unique spectrum, its own chord in the cosmic symphony. The interaction between 3I Atlas and the solar wind created its own kind of music. As charged particles from the sun struck the comet, they caused various phenomena: the ionization of gases, the acceleration of dust particles, the creation of the comet's plasma tail. These interactions generated radio emissions that we could detect with our instruments. Some comets are even known to emit radio waves at specific frequencies as they interact with the solar wind, literally broadcasting their presence across the solar system. While 3I Atlas's radio emissions were likely too faint for us to detect clearly, it was surely singing its own electromagnetic song as it passed through our neighborhood. The gravitational waves that ripple through space-time are perhaps the deepest notes in the cosmic symphony. When massive objects accelerate, when black holes merge, when neutron stars collide, they create ripples in the fabric of space itself. These waves travel at the speed of light, carrying information about their sources across the universe. While 3I Atlas is far too small to create detectable gravitational waves, it rides on the waves created by more massive objects, its trajectory subtly influenced by the gravitational symphony playing out around it. There's a beautiful phenomenon in physics called sympathetic resonance, where one vibrating object can cause another object to vibrate at the same frequency. A tuning fork can cause a nearby tuning fork of the same pitch to start ringing. A singer can shatter a wine glass by singing the right note. In the cosmos, we see similar phenomena, tidal resonances where the gravity of one body causes another to vibrate or oscillate, transferring energy through the harmony of their interaction. If 3 Atlas passes close enough to a massive body, it might experience such resonances, its orbit ringing in sympathy with the gravitational field it encounters. The search for patterns in the cosmic symphony has led to remarkable discoveries. Astronomers have found that many phenomena in the universe follow power laws, mathematical relationships that appear in music as well. The distribution of asteroid sizes, the frequency of solar flares, the pattern of galaxy clusters, all follow similar mathematical relationships to those found in musical compositions. It's as if the universe composes using the same principles that human musicians have discovered independently, creating complexity from simple rules, building elaborate structures from basic harmonies. The periodic table of elements can be thought of as a kind of musical scale for matter. Each element has its own unique properties, its own vibrational signatures, its own role in the chemistry of the universe. The elements in 3I Atlas, hydrogen, carbon, oxygen, nitrogen, and all the others, are like instruments in an orchestra, each contributing their unique voice to the overall composition. The chemical reactions that occur in the comet, slow as they might be in the cold of space, are like musical phrases, combinations of notes creating new melodies. As our ability to listen to the cosmic symphony improves, we're discovering new types of music we never expected. Fast radio bursts, brief intense pulses of radio waves from distant galaxies are like cosmic percussion, sharp notes that ring out across billions of light years. Pulsars, spinning neutron stars that emit regular pulses of radiation, are like cosmic metronomes, keeping time with incredible precision. Some pulsars are so regular that they rival our best atomic clocks, their pulses arriving with timing precise to nanoseconds over years of observation. The possibility that 3I Atlas might return adds a cyclical element to the cosmic symphony, like a rondo where the main theme returns again and again, interspersed with different episodes. This musical form, common in classical compositions, mirrors the cyclical patterns we see throughout the universe. Seasons cycle on planets, magnetic fields reverse on stars, galaxies go through periods of active star formation and quiescence. The return of 3I Atlas would be another voice in this cosmic rondo, a familiar theme coming back after a long development section. The silence between the notes is as important as the notes themselves in music, and the same is true in the cosmic symphony. The vast spaces between stars, the long periods between comet returns, the gaps in planetary rings, these silences give structure and meaning to the cosmic composition. 3I Atlas spent billions of years in the near silence of interstellar space, and if it returns, it will do so after another long silence. These cosmic rests make the moments of encounter and observation all the more precious, like a beautiful melody emerging from silence. Human music often tells stories, conveys emotions, captures moments of beauty or sadness or triumph. The cosmic symphony tells stories too, the story of stellar evolution written in the changing frequencies of variable stars, the story of galactic collisions written in the distorted shapes of interacting galaxies, the story of planetary formation written in the ordered orbits of moons and planets. 3 Atlas carries its own story, a tale of ejection and wandering, of brief warmth and long cold, of possible return and reunion. The mathematical relationships that govern music, octaves, fifths, fourths, and other intervals, appear throughout physics and cosmology. The energy levels in atoms follow harmonic relationships. The orbital periods of moons often fall into simple ratios. Even the fundamental constants of physics might be related by harmonic principles we don't yet understand. Some physicists have speculated that the universe might be fine-tuned like a musical instrument, with the constants of nature adjusted to create a cosmos capable of complexity and life. As we listen to the cosmic symphony with ever more sensitive instruments, we're beginning to hear quieter and quieter voices. The cosmic microwave background is the faintest whisper from the Big Bang, a noise floor underlying all other cosmic music. Dark matter, if it interacts with normal matter at all beyond gravity, might have its own vibrational signatures we haven't yet learned to detect. Dark energy, driving the acceleration of cosmic expansion, might modulate the cosmic symphony in ways we're only beginning to understand. The idea that Three-Eye Atlas might return suggests that the cosmic symphony has recurring motifs, themes that come back in different movements of the composition. Just as a composer might introduce a theme in the first movement of a symphony and bring it back transformed in the finale, the universe might bring Three-Eye Atlas back to our solar system, changed by its journey, but still recognizable. This would be a kind of cosmic recapitulation, a return that provides closure while opening new possibilities. The harmonics of the solar system extend beyond simple orbital resonances. There are secular resonances involving the precession of orbits, mean motion resonances involving average orbital speeds, and even three-body resonances where multiple objects participate in complex gravitational dances. Three-Eye Atlas, in its brief passage through our solar system, participated momentarily in this complex harmony, adding its voice to our local cosmic choir before departing to join other celestial songs elsewhere in the galaxy. The concept of music as a universal language takes on new meaning when we consider the cosmic symphony. If we ever communicate with extraterrestrial intelligence, music and mathematics might be our common ground. The harmonics of orbital motion, the frequencies of atomic transitions, the rhythms of pulsar signals, these are the same throughout the universe. An alien civilization studying Three-Eye Atlas would hear the same cosmic music we do, even if they interpreted it through completely different sensory and cognitive frameworks. As you drift deeper towards sleep, perhaps you can almost hear it, the vast, slow music of the spheres, the patient harmony of objects moving through space according to the ancient laws of gravity and motion. Three Atlas is out there somewhere, continuing its silent journey, its note temporarily faded from our local symphony, but still resonating in the greater galactic composition. And perhaps, in the fullness of time, we'll hear its note again, returning like a half-remembered melody from a dream, familiar yet strange, completing a musical phrase that spans millions or billions of years. And so we come to the end of our contemplation, though in truth there are no endings in the cosmos, only transformations, only new beginnings disguised as conclusions. As you lie there on the threshold of sleep, having journeyed with Three-Eye Atlas across billions of years and countless light years, having wondered about its possible return and what such a return might mean, we arrive at a truth both simple and profound. In the universe, nothing is ever truly lost, and every departure carries within it the seed of return. The comet that has left our solar system is still connected to us through the invisible threads of gravity, through the shared history written in its ice, through the questions it has awakened in our minds that will persist long after its light has faded from our telescopes. Consider what we've discovered in our journey together through these cosmic mysteries. We've learned that Three-Eye Atlas is more than just a chunk of ice and rock passing through our solar system. It's a messenger from another star, a time capsule from the galaxy's past, a reminder of the vast scales of space and time that dwarf our everyday experience, yet somehow include us in their grand patterns. We've seen how the mathematics of orbital mechanics creates possibilities for return that seem impossible, yet are written into the very fabric of space-time. We've understood that the universe operates in cycles within cycles, patterns within patterns, creating a complex symphony of motion that never exactly repeats, yet always rhymes with itself across the eons. The possibility that Three-Eye Atlas might return to our solar system in the far future is more than just a scientific curiosity. It's a meditation on the nature of existence itself. In contemplating this cosmic wanderer's journey, we've touched on some of the deepest questions humans can ask. What is the relationship between permanence and change? How do we find meaning in a universe of such vast scales? What connects us to the cosmos beyond our small planet? These questions don't have simple answers, but in asking them, in wondering about them as we drift towards sleep, we participate in the universe's own contemplation of itself. We are, after all, the universe becoming conscious of itself. The atoms in our bodies were forged in stars, just like the atoms in 3 Atlas. The water in our cells might once have been part of a comet, just as the water in 3 Atlas might one day become part of an ocean on some distant world. We're not separate from the cosmic story we've been contemplating. We're part of it, temporary arrangements of matter and energy that have somehow developed the capacity to wonder about our origins and destinations. When we observe 3i Atlas, we're really observing our extended family, our cosmic cousins made from the same stellar materials, following the same physical laws, participating in the same grand dance. The fact that we can detect and study objects like 3i Atlas represents an extraordinary achievement of human consciousness. Think about what it means that beings who evolved on one small planet orbiting an ordinary star can detect and analyze a visitor from another star system entirely. We've extended our senses far beyond their biological limits, created instruments that can see across billions of light years, developed mathematics that can describe the motion of objects we'll never touch. This expansion of awareness is perhaps humanity's greatest accomplishment, our contribution to the universe's self-understanding. But with this expanded awareness comes a kind of cosmic humility. The more we learn about the universe, the more we realize how much we don't know. 3i Atlas has raised as many questions as it has answered. Where exactly did it come from? What star gave birth to it? How many other star systems has it visited? Will it really return someday? Or will its path carry it to entirely different regions of the galaxy? These unknowns aren't failures of our science, but invitations to continued wonder, continued observation, continued contemplation. The story of 3i Atlas also reminds us that we live in a universe of constant exchange and communication, even if that communication happens on timescales that dwarf human comprehension. Every star system sends out messengers like 3i Atlas, and every star system receives such visitors. It's a vast, slow conversation conducted in the language of chemistry and orbital dynamics, a dialogue between stars that has been going on since the galaxy formed and will continue until the last star burns out. We've been privileged to intercept one small part of this conversation, to eavesdrop on the cosmos talking to itself. As we've explored the messages carried in ice and stone, the patient watching required to detect these cosmic visitors, the cycles and patterns that might bring them back, we've seen that the universe is far more interconnected than it might appear. Everything affects everything else, even if the influences are subtle and take billions of years to manifest. 3i Atlas was shaped by every star it passed, every cloud of gas it encountered, every gravitational field it traversed, and it in turn influenced all of these things, adding its small gravitational pull to the complex web of forces that shapes the galaxy. This interconnectedness extends to us as well. By observing 3i Atlas, by thinking about it, by incorporating it into our scientific understanding and our cosmic mythology, we've become part of its story. The comet is now part of human culture, part of our collective memory. Children learning about astronomy will hear about the interstellar visitors we've detected. Scientists will use data from 3i Atlas to test theories and develop new ones. Science fiction writers will imagine stories of interstellar comets carrying messages or life between the stars. In this way, 3i Atlas has achieved a kind of immortality in human consciousness, even as it continues its physical journey through space. The question, what if 3i Atlas comes again, is really a question about hope, about the possibility that the universe offers second chances, that connections once made are never truly broken. In our personal lives, we often wish we could revisit moments from our past, see old friends again, return to places that were important to us. The possible return of 3I Atlas suggests that on cosmic scales, such returns are not just possible but perhaps inevitable. The universe has a kind of memory encoded in the trajectories of objects through space, and given enough time, paths that diverge might converge again. But even if 3I Atlas never returns to our solar system, even if its path carries it to entirely different regions of the galaxy never to return, its visit has been meaningful. It has shown us that we're not isolated, that material and information flow between star systems, that the galaxy is a more dynamic and interconnected place than we might have imagined. It has given us a glimpse of chemistry from another star system, a sample of the diversity that exists among the galaxy's billions of planetary systems. Most importantly, it has reminded us to keep watching, to stay curious, to remain open to the wonders that might appear in our skies at any moment. The universe doesn't owe us answers to our questions or resolutions to our mysteries. It simply is, vast and ancient and indifferent to our desire for understanding. Yet in that very indifference lies a kind of invitation to find our own meaning, to create our own understanding, to write our own stories onto the cosmic canvas. 3 Atlas doesn't care whether we observe it or not, whether we wonder about its return or forget it entirely. But we care, and that caring, that wondering, that reaching out with our minds to grasp something so far beyond our physical reach is what makes us human. As sleep finally claims you, carrying you off into your own nightly journey through dreams and darkness, remember that you too are on a cosmic journey. The Earth carries you around the Sun carries you around the galaxy carries you through the universe. You're a traveller on multiple scales simultaneously, just like 3I Atlas. And just as the comet might one day return to our solar system, you return each morning from the mystery of sleep, changed by your dreams, but still yourself, ready to continue your own exploration of existence. The questions we've explored tonight don't have definitive answers, and that's as it should be. The universe is too vast, too complex, too wonderful to be fully comprehended by any single mind or even by all minds together. But in wondering about 3I Atlas, in imagining its journey and its possible return, we've participated in something profound, the universe's contemplation of itself, consciousness reflecting on the cosmos that gave rise to it. This is perhaps the deepest mystery of all, that the universe has evolved creatures capable of wondering about it, of finding beauty in the motion of distant comets, of feeling connected to objects they'll never touch. 3 Atlas continues its journey through the darkness, carrying within its frozen heart the secrets of another star system, the memory of its brief warming in our sun's light, the potential for future encounters we can only imagine. Whether it returns in 1 billion years or never returns at all, it has already achieved something remarkable. It has expanded our awareness, enriched our understanding, and reminded us that we live in a universe full of wonders waiting to be discovered. And so we end where we began, with a question that opens rather than closes, that invites wonder rather than demanding answers. What if 3I Atlas comes again? What if the universe is full of cycles and returns we haven't yet recognized? What if every departure is also a promise of return, even if that return takes longer than civilizations last? These questions accompany you into sleep, into dreams where time and space follow different rules, where journeys that take billions of years in waking life might unfold in moments, where comets might sing and stars might dance, and the impossible becomes beautifully, wonderfully possible. Rest now, knowing that while you sleep, the universe continues its patient unfolding. Somewhere out there, 3I Atlas continues its journey. Other interstellar visitors approach our solar system, still undetected but coming nonetheless. The great cycles of the cosmos turn on, marking time on scales we can barely imagine, and tomorrow, when you wake, the universe will still be there, still full of mysteries, still inviting us to wonder, to watch, to imagine what cosmic surprises might be heading our way. The story of Three-Eye Atlas is far from over. In fact, it has barely begun. We've witnessed just a brief chapter in a tale that spans billions of years, and there are countless chapters yet to be written. Perhaps one day, in the unimaginably distant future, conscious beings we cannot envision will detect a familiar visitor approaching their star system. They'll analyze its composition, calculate its trajectory, and realize with wonder that this comet has been here before, long ago, when their star was young and their worlds were different. They'll understand that they're witnessing a cosmic return, a closing of a circle that began before their species existed. And in that moment of recognition, across all the vast reaches of space and time that separate us, there will be a connection, a shared wonder at the patient movements of the cosmos, a common appreciation for the beauty of celestial mechanics, a mutual recognition that we are all, every one of us, part of something infinitely larger than ourselves. Three-Eye Atlas, in its silent journey through the darkness, carries this connection with it, a bridge between past and future, between here and elsewhere, between what is and what might be. So sleep peacefully, dream deeply, and remember that you are part of this cosmic story. The atoms in your body have been on journeys just as epic as Three-Eye Atlas's voyage. You're made of cosmic material, shaped by cosmic forces, participating in cosmic cycles. And tomorrow, when you wake to continue your own journey through space and time, you'll carry with you the wonder of these cosmic mysteries, the questions that have no answers, the beauty of a universe that never stops surprising us with its depth, its complexity, and its infinite capacity for wonder. What if Three-Eye Atlas comes again? We may never know, but in wondering, in imagining, in hoping, we become part of the cosmic story, adding our voice to the eternal conversation between consciousness and cosmos, between the observer and the observed, between the questioner and the infinite mystery that invites our questions. And that perhaps is the most beautiful mystery of all, that the universe has given rise to beings capable of contemplating it, of finding meaning in the motion of distant comets, of dreaming about returns that may never come but are wonderful to imagine nonetheless. Forever and always the cosmos continues its dance, and we dance with it, small but significant, brief but memorable, alone but connected to everything that has ever been and ever will be. And somewhere in that vast dance, Three Atlas continues its journey, a frozen wanderer carrying messages we've only begun to decode, following a path that might, just might, bring it home again.